Okay, a very good morning, everyone. Welcome back to another HSMA training day. So today we're going to be looking at agent-based simulation. So carrying on from the very first session we did in this module on cellular automata, which was a lot more sort of theoretical and quite abstract in terms of the things we were talking about. I hope quite interesting though. I found it quite a magical sort of concept, I think, cellular automata. But what it hopefully did was to introduce you to some of the key concepts behind agent-based simulation. And a cellular automaton, as we discussed in the session, is kind of the purest distillation of an agent-based simulation. But today's going to be much more practical, and it's going to be focused on showing you how to build a real-life agent-based simulation. Specifically for modeling a disease outbreak using MESA, which is a really nice package actually in Python I came across a few years ago, that makes things very easy to code in an agent-based simulation in Python, because it takes away much as SymPy takes away you having to code everything from scratch. MESA does the same, but I think MESA's a lot more friendly actually than even SymPy. And so hopefully those of you who came along to the session yesterday afternoon, I know that was a very intense session, so please be assured I think you'll find today a lot easier. MESA's a lot easier to get to grips with. MESA is also a really nice way, and agent-based simulation more generally is actually a really nice way to cement your understanding of object-oriented programming, because object-oriented programming and agent-based simulation are kind of made for each other, because it's all based based simulation is all based around concepts of having individual objects that have certain properties, i.e. attributes, and can do certain things, i.e. methods. So it really helps you to understand object-oriented programming as well. So you get a sort of double benefit from this, and I think it's a really nice way to learn it. So that's what we're going to be covering today. So we're going to be using the MESA package. I'm going to be talking you through this model, and then this afternoon we're going to cover a little bit more on some of the features of MESA. But then this afternoon you're also going to get a chance to design and build your own agent-based simulation. So whereas in the cellular automata session you came up with some great ideas in the groups about things you could do, and a lot of you are actually moving beyond cellular automata and thinking about agent-based simulation-y type things. And I know a lot of you were frustrated because you wanted to be able to then build them. This will allow you to build them. So by today, at the end of today, you'll be able to build, hopefully you'll be able to build little prototypes of what you designed last time. That's the idea for this afternoon. Okay, let's plow on. So let's just remind ourselves what we mean by agent-based simulation. We touched on it a little bit in the cellular automata session, but let's describe what we mean by agent-based simulation more generally. So it's basically a simulation method that focuses on behaviors, interactions, motivations, goals, etc. of various individuals. And you're looking, remember, we talked extensively in the last session about how we're interested in the kind of complex emergent behavior that arises from these kind of individual level interactions, which are often very, very simple, but then you have this sort of complex, interesting emergent behavior emerging. And we also touched on how it's commonly used in ecology, where it's known more often as individual-based modeling, where particularly in things like ecological foraging models, where you often know a lot about how an individual forager behaves, but you don't know so much about how they behave at a population level. It's also been extensively used in modeling disease spread and outbreaks in public health. And as we saw last time, it's quite different to conventional mathematics, and has these sort of interesting properties and these interesting patterns that emerge in the natural world. So let's think about the elements of an agent-based simulation. So the first element, probably the most important, I would argue, is the agent. So we have agents that are basically moving and interacting in some way within and with an environment. So the environment's where they live, and the agents are moving around in that, and they're interacting with the environment, and they're interacting with each other. We've got individual level behaviors and interactions. So we describe everything at the agent level. And the outcome, the thing we're using the model or the simulation to explore, is the emergent behavior. That's what we're interested in. So we're kind of putting in individual level rules and seeing what comes out at a system level and at emergent population level. So we touched on last time when we looked at cellular automata, Conway's game of life, this idea that you can have a grid of cells and just really force really simple rules where a cell will live or die in the next generation, just depending on its current state and the current state of its neighbors. And as you saw, you got these fantastic complex phenomena emerging, including these life forms that seem to emerge, things like spaceships and gliders and all sorts of fascinating things, just from these really four simple rules. So I'm going to touch on a little bit. So my PhD was in ecological modelling using individual agent-based simulation. Obviously, I called it individual-based modelling because I was in ecology then. If you want to read all about it, please do purchase this book. This is a blatant plug. You can purchase it. It's just the bargain price of £69 on Amazon. This book has been flying off the shelves for the last 10 years. It's sold over 1 copy. And I think if I get 5 copies sold in a year, I think I get something like 50p off a book. So you know, these are high stakes. If you don't want to buy the book, you could just read it for free online, because my thesis is also published there. But I'm going to give you a little bit of an introduction to what I did, because it'll help you to understand, although this is ecological modeling, it'll help you to understand a little bit about how you can use agent-based simulation or individual-based modeling. So the project I was doing for my PhD was known as Harvest, which was harvesting animals with reinforced values and estimates. Basically, the idea was we wanted to create a model of the way in which bumblebees forage in large-scale landscapes. Now, bumblebees are significant pollinators within landscapes. They travel extensively, and they are very significant pollen vectors. And there was a concern that as genetically modified crops began emerging within landscapes, that there would be a risk that bumblebees would essentially sort of cross-contaminate by spreading GM pollen to non-GM fields. And so because they travel such large distances, and so we wanted to build basically a model to try and work out what happens. We know a lot about what happens as they in terms of individual behaviors when they forage, but what happens when you sort of scale that up at a population level. So we built an agent-based simulation to do this. And it uses something called reinforcement learning, which we taught last year in HSMA. We didn't this year, but we've got videos on it if you're interested. And reinforcement learning, I think we touched on a little bit in the first machine learning module, is basically where you're trying to learn by doing, and you gradually learn to do things where you get rewarded and avoid things where you get punished. And it's a really good kind of Swiss Army knife of machine learning, and has a huge potential. And of course, it's the way in which animals learn within nature. So is a very good thing to include in a model like this. But basically, we had individual little artificial bees, and they had a goal, and their goal was to fill up with nectar, their food, as quickly as possible, because we know that bees are motivated, they're energy motivated. They have to be consuming food at all times, sound like me, and they very quickly will run out of energy if they're not consuming food. So they need to try and minimize their energy expenditure but maximize their kind of gain from food. So we had bees essentially with this goal as individual agents, and then they would be presented with a choice of fields within the environment. Each field would have a number of flowers, so every time a bee would enter a field, it would randomly choose a flower to sample, and that flower would either have nectar in it or not, so just be a binary flower essentially, and then it would either choose to stay in the current field or move to another field. And if it stayed in the current field, it would randomly pick another flower. And so each field would have a percentage of fullness. So in other words, what's the probability that a bee sampling in this field will get some food. But the bee doesn't know what the true percentage is, but it does maintain an estimate. So it'll have, and this is where the reinforcement learning comes in, it'll have a sort of an idea about how good it thinks this particular field is. And there'll be travel times between these fields as well. So essentially what it's doing is making trade-off decisions. So it's constantly trying to sample food. And every time it samples a flower, it either gets rewarded or punished by having no food. And it adjusts its estimate of that field. And so essentially it's trying to make the decision, should I stay here and just keep trying, or should I try my luck somewhere else and take the kind of travel cost hit, but take the risk that it might be even worse? And so they're constantly trying to make those decisions. And so, I mean, to cut a long story short, with the conclusion of this model, we tested it empirically as well. So I stood for a week in Exeter with 6 trays of oilseed rape flowers, and wheeling them in and out from a greenhouse as students walked by every day. And I very quickly descended into madness and started talking to the bees, and just stood there with a dictaphone saying B4 has now arrived at patch A, again and again and again. And the beauty of that was it turned out that our model was actually a really good predictor of what they would do. So we tested then the model, gave it the same setup, and saw how they behaved, and they behaved in a very, very similar way. And so it turned out this was a really good, even though these were really simple rules that we'd put in, it was actually a very good predictor of real bee behavior. And it turns out basically that bumblebees are a potential risk, but because they tend to stay so long in fields, because they're risk averse, and so they tend to try and stay where they are where they can, you get a dilution effect of the pollen, basically. So you don't tend to get much risk from cross-contamination. But we did come up with a fantastic strategy, which was, if you're really worried, you could have a sacrificial shield of crops. You basically surround your non-GM crop fields with some plants you're willing to sacrifice, and that completely protects them. So yeah, really interesting strategies that you can come up with in this stuff. But the key thing I wanted to sort of convey from this was this idea that you could have these sort of individual agents that are operating with pretty simple rules, acting in an environment, but we have this interesting population level dynamics that were emerging, and that's what we were interested in. Okay, so let's talk about MESA. So MESA is a Python-based framework for developing agent-based simulations. Much like SymPy is a framework for discrete event simulation, MESA is very similar. I'd argue actually MESA's got a lot more user friendliness, and certainly very good visualization capabilities, which obviously SymPy doesn't have. And it's actually a really nice package, and it's free and open source, of course, because we're teaching it. And it's really quick and easy to put together these models, as hopefully you'll see today that you can actually put together some really nice models, and you can see how you can extend stuff really easily. It's very, very logical how you use this. So hopefully you've all managed to get MESA installed. We just use a pip install as normal for MESA. So I'm going to talk a little bit about the model structure, how we structure a MESA model first of all, because this can seem a little bit more odd, but hopefully this will make sense. Basically, when you develop a discrete event simulation, for example, in SymPy, you've been used to just having a single .py file for that. With MESA, you have 3 .py files, and each of these is a module, and each of those .py files does a separate thing. So you have one which is for your model, Okay, and the model one is the main one. That's going to describe how your model works. So that's where you do the main coding for your model. Then you've got a separate one called the run module, a separate .py file, and that will basically run the model, and it will choose how that model runs. And then you've got an optional server module, which you don't have to have. You could just have these two. But we're going to see have a look at this because it's a really nice way. And what it does is it basically launches a JavaScript, launches a server and uses JavaScript to basically draw the model live in a web browser, so you can watch the model unfold. Now, some of you we did have some issues last year where, depending, because you have to basically open network ports. Most people were fine, but a few people this didn't work. I'm hoping though that at least one person in your group this will work for when you come to do this. But don't worry if not. If it's an absolute, this isn't essential, but it will be quite a nice way to play around with it. So in the model module, so the model.py file, we're basically going to have a number of classes and some separate functions. So we're going to have a class for each type of agent. Now, normally you'd probably only have one type of agent, but you can have more than one. So you'd have a separate class for each agent type. And that class will contain any relevant agent attributes. It'll have a constructor method. It'll have methods that define the things that the agent can do, moving around the environment or whatever else they may do. And it'll also have a step method. And that step method will define basically what actions it will take in which order. So it'll say at each step of the model, each time step, do this, then do this, then do that. Okay. So you have a class for each type of agent. We're only going to have one agent type in the model you're going to be building today. So you just have a single class for that agent. Then we're going to have a separate class for the model. And the model class will basically have the relevant attributes describing the model, a constructor method, obviously, and it'll also have its own step method that defines what happens model-wide at each time step. So that will control the model at each time step. And then separate to those classes, we'll have some functions that will basically calculate some results. So that's the model module. And then the run module, as I say, will describe whether you're going to run this thing either as individual runs that you can watch, or whether you want to run them as batch, and whether you want visualization or not. And then the server module, which is optional and allows you to view it in the browser. And basically, because each of these modules lives in separate, so we'll have 3.py files, we basically import the modules and the bits of modules that we need into each. So in the server module, we'll import bits of the model module that we've written that we need for that particular server. This will all make sense when you come to see it. Okay, so here's what we're going to do. So imagine we've been asked to model the spread of a new disease. Now, this disease is spread through close contact with infected individuals. The probability of someone catching the disease after coming into contact with an infected individual, which is known as the transmissibility, is 20%. And the disease lasts on average for 10 days. So we've got people who are infectious, and if they come into contact with an uninfected individual, there's a 20% chance that they will pass it on. And on average, the disease lasts for 10 days, although obviously there'll be some variability in terms of how long it lasts for particular people. So what we're going to do is we're going to build up a model of the spread of this disease within a population. This is a classic way in which we can show you how an agent-based simulation works. Okay, so the first thing we're going to do is to import the libraries that we need to build a model. So I'm going to flip over to Spider. Here we are. Okay, so we can see at the top, what we're going to do is we're going to import the libraries that we want. So these are the libraries from MESA that we're going to import. So the first thing we do is we import from MESA. We don't import all of MESA, we just import bits that we need. We're going to import the concept of an agent, and we're going to import the concept of a model. Those two things you're going to need. So those are the agent class and the model class. And that allows us to not have to start from scratch and describe what an agent is and what a model is. It already knows those things, so we can just use these concepts. So that makes it really easy for us to then build our agents and build our model. We're also going to import these extra little things here, and the specifics of this will depend on the model you're doing, and this will make more sense as we go through it. But I do love the names of this. So from MESA.time, we're going to import something called random activation. That basically means that we're going to randomly order the order in which agents act, and we'll come back to that in a bit. From MESA.space, we're going to import a multi-grid. So a multi-grid, obviously all your agents will live on a grid. A multi-grid is basically a type of grid where you can have multiple agents per cell. So there are types of grids where you can only have, one cell, and you can only have one agent per cell. But here we've got a multi-grid where we want more than one agent per cell, because that's when people will be in the same location, and potentially they will then be able to interact and infect. And we're also going to import from MESA data collection something called a data collector. We will come back to that later, but they're a really nice way in which you can grab results out really easily, much easier than something like SymPy, the results that you want to grab out from your model. And we're going to also import the good old random library, because remember we said that we're going to have the disease will last on average 10 days, but there'll be some variability. So we'll use a distribution to work out precisely how long somebody has the disease. Okay, so that's the imports. So next we're going to go on to writing the agent class. So for this model, we're just going to have one type of agent. So we only need a single agent class, and this will represent a person. So we've got a person agent in our model. So what we're going to do in our agent class, we're going to have multiple functions that define what an agent does. So we're going to have a function that tells it to move. We're going to have a function where it can infect others, and a function to define all of the things to do at each tick of the clock, i.e. the step function. So we'll have all that. So basically agents will be able to move, they'll be able to interact with each other by potentially infecting or being infected, and they'll have a step function which will describe all the things, the order in which things happen. But remember, because this is object-oriented programming, we must first define the constructor in it. And in the constructor, we're going to specify the transmissibility, the level of movement of the agent, the average disease duration, and whether or not the agent's infected at the start of the model according to some sort of probability that we specify. Okay, so where are we going? So let's have a look. Probably easier to look at it in here. So this is the constructor. So I've first of all, let's start with the class definition here. So I've called my agent a person agent. Obviously, you can call it whatever you like, but I've made it clear that it's an agent class, and the agent is called a person. Now, one thing you'll note here, and hopefully you'll remember this from your Python coding sessions, I've passed in an agent to this class definition. Now, remember, we imported the agent class from MESA. And now if you think back to our object-oriented programming stuff, we talked about inheritance, and we said inheritance is a really useful feature of object-oriented programming, because basically what it allows us to do is to say, create a new class and say this class is like one of these, but it's just got these differences. And so this becomes the child class that inherits from the parent. And so the beauty of this is that we can inherit from the agent class, and the agent class from MESA is where they've described everything about being an agent. So we don't have to do all that from scratch, and it'll already know concepts, and we can use that to our advantage. Otherwise, as I did for my PhD, you'd have to code everything from scratch. You'd have to define what an agent was and what it meant to move an agent and all that sort of stuff. You don't need to do that here, because it's done it for you. So we can just inherit the agent class. So then we're going to set up the constructor. So these are the things we're going to pass in. Obviously, we always have to pass in self first, the copy, the instance of this object. Sorry, this class. I'm going to pass in a unique ID just so we can keep track of each agent can have its own ID. I'm going to pass in the model. That's the model in which they're going to live. The initial infection, that will basically determine the probability that they are infected at the start of the model. Transmissibility, remember that's the probability that they will, if they're infected, that they will pass it on to someone else. the level of movement, which is basically just a probability that at any given time step they will move. So obviously the higher that is, the more they'll move. And the mean length of the disease. So on average, how long do they have the disease? So the first thing we're going to do, because this is inheritance, we're inheriting from the agent class. The first thing we're going to do is use the super method. Now remember, we can call this to say basically, just call the constructor from my parent, in this case the agent class, and do all of that. So set up all of that, okay? And this is the reason why we've got the unique ID and the model, because that's the two things that the agent class needs. It needs to have a unique ID for a particular agent, and it needs to have the model in which they live. So we need to pass those two things to the parent constructor. And then it'll do everything. So this will set up all the magic of MESA, and it'll do all the stuff. It'll set up what an agent is, and then we can just focus on what we want to put in for our particular agent. Okay. So this will do all the hard work for us. So next we're going to basically set up our attributes. So remember, when we're doing object-oriented coding, we set up our attributes in our constructor. So this should look pretty familiar to you. So I'm going to set up a transmissibility attribute within the person agent class, and that's going to be, I'm going to set that to whatever transmissibility I've passed in. I'm going to do the same with level of movement. I'll do the same with the mean length of the disease. So we've got transmissibility, level of movement, mean length of disease have been used here. So they've been used to set up the three attributes in that person agent. We've used unique ID and model, which we've passed over to the parent. And then this last one is the initial infection. So this is, remember, this is the probability that the agent is going to be infected already at the start of the model. And we want our model to have some infection at the start. Otherwise, we're going to be watching a very boring model where nobody gets infected because there is no pandemic. So we're going to set that up now. What we want to do is to basically use this probability to just determine whether this agent will be infected or not at the very start of the model when it's created. So we've passed in this initial infection. That's our probability. Now you'll be familiar with doing this now. What we can do is we can take a sample from a uniform distribution. So basically just random pick a number between 0 and 1 with an equal chance of any number being picked, and then compare that to the initial infection probability. And if it's less than that, then we can say that that infection has happened. So if it's a 30% chance that they're initially infected, then there's a 30% chance that a number between 0 and 0.3 will be picked. And so if that happens, then they will be infected. So we look at that. If they are infected, then what we're going to do is to set up an infected variable, infected attribute against this person agent. And that's going to be a Boolean. So basically, they'll have an attribute. Each agent will have an attribute that says whether they're infected or not, and it'll either say true or false. So if they are infected at the start, we need to set that to true. And because they're infected, we need to work out what their remaining disease duration is, because we need to work out how long they're going to have this for. So the way we're going to do that, we're going to set up an attribute called disease duration. And remember that we said that on average it'll be 10 days, but that may there'll be some variability around that. So we've passed in the mean length of the disease. So we're going to just use an exponential distribution here, much as you've been using for SymPy. And we're just basically going to pass that in, take 1 over the mean because we're giving lambda here. And we're going to round that to 0 decimal places, just to make sure that we're only dealing in whole days. Okay, so that will basically determine how many whole days they will have the disease for. If we determine that they're not infected at the start of the model, then we'll just set their infected their little Boolean flag here to false. So it'll either be true or false at the start, depending on whether they get chosen to be infected. But if they are infected, then we additionally work out how long they're going to have the disease for. And that's it. That's the entire constructor. Okay, so all we've done in the constructor, so we've set up the person agent, we've passed in the agent class from MESA that we've imported. That will do all the magic for us. Then because it's inheritance, we're going to call this the super method, which will basically call the constructor in the parent class in agent, pass it over an ID for the agent and the model, and then just set up the bits we want for our particular problem. So we'll set up a transmissibility, a level of movement, average length of the disease, and then we'll work out whether or not they get infected at the start. That's it. Okay, so whenever a new agent is created, this will be called. Okay, so next let's think about movement. So we want our agents to move around our environment. If they don't move around, we're not going to get any infection, because unfortunately that's how viruses spread. So we need to write a movement function in the person agent class that will specify how our agents are going to move around our grid of cells, our environment. So in this model, what we're going to have, just for simplicity, we're just going to have agents who will randomly move to one of their neighboring cells. We're going to use a more neighborhood, which, if you remember from the cellular automata session, basically means all of the 8 neighbors, the 8 surrounding cells, and we're just going to choose one of those cells at random. Now, obviously, if you were doing this for real, you may have you may not just want random movement. You might, it depends what you want to do, but you may have some more detailed information about how people might tend to move, depending on what your agents are and what your environment is, and so you could set up different patterns. But here, just for simplicity, we're just going to assume some sort of random movement. So what we need to do, we first need to work out when an agent is going to move, what the possible movement locations are based on the cells around the agent. We're then going to pick one of those at random and then tell the model to move the agent to that cell. Okay, so really easy. That's all we're doing. If the agent decides to move, then it's going to work out here. Essentially, here are the cells I could move to. I'll pick one and I'll move to it. That's all we've got to do. Okay, and because we're using MESA, all of those concepts are baked in, so we don't need to worry about describing concepts of moving in a grid. So let's set up another method within our agent class. This one we're just going to call move, nice and self-explanatory. And we're only passing in self to this. We don't need to pass in anything external. So this is basically the agent movement method. This will be called if it's determined that the agent is going to move. So this won't get called. So basically the decision about whether they move or not will be made elsewhere. So this method describes what happens if it's determined they are going to move on this time step. So the first thing we're going to do is we're going to get a list of the possible neighboring cells. Okay. Now this is really easy because we're using MESA, that we can use various methods of the grid within the model. So what we can do to get a list of our neighbors, we can call self.model. So remember, the agent has a copy of the model that it lives in. So the model it lives in dot grid, which is describes the grid that there is our environment, and then we can call the dot get neighborhood method of the grid. And this method, the dot get neighborhood method, basically returns the neighbors for this particular cell. So we need to just pass 3 things in here. We want to pass the location for which we want to get neighboring cells. Well, the location is wherever this agent is. So where am I now? And we can do that just by saying self.pos, and that stores the current location. Which cell am I in now? We also need to pass in what type of neighborhood, whether it's a more neighborhood or not, which this one is. Remember, it's going to include the diagonals. So it's all 8 neighbors. So we say more equals true, and include center equals false, because we don't want to include in that list the center cell, because that's where the agent is. We don't want to, if they're going to move, we don't want the cell where they currently are to be a valid location. Otherwise, they won't move. They'll just move to the same place. So we only want to include the 8 neighboring cells. So if we call that method by giving the location, which is our current location, the type of neighborhood, and that we don't want to include the center, this will then be returned as a list possible steps here, and this will basically be a list of cells that it can move to. Then all I need to do is pick one at random. Remember, we can use the random.choice to randomly pick something from a list. That's all I'm doing here. I'm saying random.choice on possible steps. I'll randomly pick one of those cells, and that will be my new position. So I'll store that. So then all I need to do is move. And I can do that really easily because I'm using MESA, and I just call the .moveAgent method of the grid. And all I need to pass that is self and the new position, so wherever I want to move to. So all I've done in this method is to work out what possible cells I can move to, then pick one of them at random, and then move to it. That's all I've done. Okay, and that's movement. And because it's MESA, I can use these handy little methods to get my neighboring cells or to move the agent. It'll do all that for me. Okay. So that's moving. Now, of course, another key behavior in a disease model is infecting. So in our model, people can infect other people, and we need to write a method to specify how this will work. So how it's going to work for our model is if a person's infected and they're in the same location, the same cell as non-infected people, then there's a probability that each of those non-infected individuals will be infected. That's the transmissibility. So if I'm infected and I'm in a cell and there's two other people in that cell with me and they're not infected, and so the transmissibility is 20%, then there's a 20% chance that each of those will be infected. So what we're going to do to emulate that is we're first going to get a list of all of the agents in the current cell. We need to check who's in there with me. If there's more than one agent in that cell, i.e. more than just me, then we're going to go through each agent in that cell, and if they're not already infected, then we'll randomly infect them according to this transmissibility probability. And if they do get infected, then we'll also randomly sample how long they're going to have it, i.e. their disease duration. Okay, so that's all we're going to do. So let's look at the infect method, this one here. So I've just called it infect. Again, we don't need to pass anything in other than self. So the first thing we do, remember, we need to find out how many, who's in this cell. Okay. So we can get a list of agents in any current cell in MESA just by calling the get cell list contents method of the grid. And all we need to pass it is a position, i.e. the cell that we want to get the agents, the contents for. So we need to pass that in as a list, even if there's only one entry. And there is here, all I'm passing in is basically my current location because I want to find out who's in my cell. So that's the thing that I pass in. That will then return a list of cellmates. Okay, so that will be a list of the agents as objects, a list of the agents who are currently inhabiting the cell I'm in. Now I need to check if there's more than one, because if there's only one, if the length of that list is one, then it's just me, that I'm the only cellmate in there. Sorry, the only agent in there. But if there's more than one, there's somebody else in that cell with me. And so if that's the case, then I need to determine if I'm going to randomly infect them. So what I'll do, I'm just going to go through a little for loop. Okay, so I'm going to say for each inhabitant in cellmates, in other words, for each agent in this cell, there may only be one, that's fine, but there may be loads. But for each one, I'm going to see if they're infected or not. So I can have a look at their infected attribute. Remember, each agent, because we set it up here, when they get created, they'll have an infected attribute, and that will either be true or false at the start, and that will change over time, depending on if they get infected. So we can check to see if they are currently infected by checking that infected attribute. If that's false, then they're ripe for infection. We can infect, obviously, if they're already infected, if that's true, then we just move on. We don't do anything because we can't infect them again. But if they're not infected, then there's now a chance that we're going to infect them because we are infected. And so if they aren't infected, we're going to randomly pick a number between 0 and 1 on the uniform distribution and compare that to our transmissibility. So if it's 20%, 0.2, we'll randomly pick a number. And then if it's less than that, 0.2, then we're going to infect that cellmate. So the way in which we infect them is we set their infected attribute to be true, and then we work out how long they're going to have the disease for and store that. So basically, you're going through each agent in that cell that's not you, and you're seeing if they're well, actually, technically, you are. Sorry, let me be clear. If there are 3 of you in that cell, one of the iterations in this for loop will look at yourself, because you're looking at all of the cell, but you won't, because you're already infected. If you've gone through this method, nothing will happen because you're already infected, so it won't get down to this bit. But basically, you're looking at each inhabitant in that cell. If they're not infected and you are, then there's a chance you'll infect them. And if they do become infected, then basically what that means in the model is their infected attribute becomes true, and you calculate a disease duration for them, which you randomly sample from an exponential distribution. Okay, so that's it. That's how we infect people in this model. So now we've got all we've done is we've written an agent class where we've got a constructor that sets up those attributes and works out whether they're going to be infected at the start or not. We've then got a move method, which will basically determine what happens if they move. So if we determine they move cells, then it'll get a list of where they can move. It'll set to one of those cells at random and it'll move them. And then we've got an infect method, which will basically see if there's anybody else in that cell. And if there is, and this method is called, that means they're infectious. And so it'll then randomly determine whether they get infected and then infect them. Okay, so that's all there is to it. That's all we've defined there. So the next thing we need to do is well, actually, before we do that, any questions so far? No? Good. Okay, hopefully it's all making sense. As I say, I think it's a little bit more straightforward than some of the other methods you've used. So the next thing we've defined our constructor. We've defined the kind of behavior methods for moving and interacting. And the last method we need to write for the agent class is the step method. Remember, that's the one that's basically going to specify the series of things that an agent will do at each time step. Okay, so here in our model, our agents might move, they might infect others if they're infected, and they might recover if they're infected. Okay, so these are the 3 things that can happen. So what we need to do is we need to first check whether the agent's going to move on this time step. Remember, we've got a level of movement probability that determines that. Then we're going to determine if the agent is infected. We're going to check if the agent is infected, and if they are, then we're going to call the infect function that we've just written, and that will potentially infect others. And we're also going to, if they are infected, we're going to decrement the disease duration by 1 time step. So if they've got 10 days remaining, they've now got 9 days remaining, etc. Okay, so move, infect, get better is the slogan that we're going to use here for our model. So that's what we want to put in here. I say we. I'm going to now ask you to do this. So first exercise, I'm going to put you into your groups. What I want you to do, I've given you the file disease model x1.py. So let me just bring that up a moment. No, not that one. This one here. Okay, so this has got in it everything that we've written so far. So this is what I've just shown you. Okay, and nothing else. So what I want you to do is to use that file, and I want you to write the step method of the person agent class. Okay, so you can add another method into this agent class. And what the method should do, first of all, it should randomly determine whether the agent's going to move on this time step, and that's based on the defined probability of that happening. Remember, we've got a probability that the agent has of moving on any time step. If it's determined that they should move on this time step, then make that happen. Then you need to start infecting any other agents that are in the same cell, but only if this agent is infected. And if the agent is infected, you also need to look at their remaining disease duration and decrement it. And also check if the disease has now run its course, i.e. there's no longer a disease duration, then that needs to be updated in the agent's attributes too. So your code should run without errors, but it won't visibly do anything, because all we're doing at this stage is just defining a person agent and importing some libraries. So it won't appear as though it's done anything, but if it runs and there are no errors, that's a good sign. Okay. So I'm going to give you until about 1:45-ish to do that in your groups. I'll be a bit more generous, let's say 10 to, and give you a chance to have a 5-10 minute break as well. So have a go at your group, go into your groups, have a go at that and take a break, and we'll resume at about 10 to 11. Okay, right, I'll stop there and open the groups. Hi everyone. Okay, so I hope you all had a go at that. I bounced around quite a few of the rooms and looked like you're all on the right lines, which is good. So hopefully that's a good sign. I'll just quickly show you the solution. So it wasn't too complex. You probably thought it would be more complex than that, but it's not. And I'll just flag up a couple of things that came up. Where am I doing? Share screen. Okay, right. Let's bring up the solution. So here's the step method, and you may have done it slightly differently, but this is basically the basic structure. So I've defined my step method, I call it step. First thing we need to do is determine if it's going to move, and remember the movement is determined by the level of movement, which is a probability. So basically that probability is the probability that any given agent will move at any given time step. So we're just going to take a random sample from the uniform distribution and check it against the level of movement, which remember is stored as an attribute of this agent. So what you're essentially saying here is take a random number between 0 and 1 and see if it's less than the level of movement that I've got stored against myself. Okay, that's the self bit. Remember, self is a bit like saying me. What have I got in my attributes? And then if that comes out to that is less than the level of movement, in other words, we've picked a number, we've met this probability description, then I'll just call the move method on myself. Okay. Then we need to check whether I'm infected or not, because if I am infected, there's a couple of things I need to do. If I'm not infected, I don't need to do anything, so I don't need anything else. So I'll check if I'm infected. So again, I'll check my infected attribute. So self.infected, that infected attribute that I've got, is that true? If I am infected, there's a couple of things I need to do. I need to call the infect method. That doesn't necessarily mean that I will infect other people, because remember, the infect method will determine if there's anybody else that isn't infected that I'm sharing a cell with, and then it'll determine randomly whether I infect them. But I need to start that process if I am infected. And I also need to decrement my remaining disease duration by 1 time unit. So I grab my disease duration from my attributes and I just subtract 1 from it, because our time unit's days here. What I also need to do is check to see if the disease has run its course. So if I am infected, now that I've taken 1 off the disease duration, has my disease now run its course? Now, a lot of people quite rightly and understandably put if self-disease duration is strictly equal to 0. Now, one thing you may want to be careful of here, and the reason I've put less than or equal to 0, and I noticed at least one of the groups picked up on this, because we're actually we're using an exponential distribution here for simplicity. That may not be what you use in reality. It depends on what you're modeling, but we're just using an exponential distribution because it's easy to play with. There's a possibility that you could end up, because it's rounding it to 0 decimal places, so it just round to the nearest whole number. You could get a very low disease duration when that's determined, when they first get infected, and it could then round to 0, which means you could have somebody who's infected but has got a 0 disease duration, which means that they can still possibly infect people for a time unit. And that kind of makes sense when we think about it, because they may, if they did have a very short disease duration, unlikely as that would be, they would still be infectious for a period of time. And our kind of atomic unit here is a day. So they're going to be infectious for at least that 1 time unit. So the way we can deal with that here, because obviously if they had a 0 disease duration, when it gets to this point, it'll take 1 off and you could end up with a disease duration of -1. So this just catches that possibility. In reality, probably a better way to do this would be to catch it here. so that when you first set up the disease duration, if it does come out to be 0 when you round it, you could just say, well, make that 1, because the minimum disease duration is going to be 1. Okay, so you could, it'd probably be better to deal with that there. Although I'd probably still include a less than or equal to here, just in case something goes wrong. So it's worth maybe catching that. But that's all there is to it. Okay, so all you've done in the step method is determine if they're going to move, and then call the move method if they are, and then check if they're infected, and then if they are, call the infect method that we've written, decrement their disease duration by a day, and then check if their disease has now run its course. And if it has, just update their infected attribute to false. Okay. Any questions about any of that? No. Good. Okay. As I say, it's not complex, and that's, so basically we've written our agent class. That's it. That's all we need to do for the agent class. And it's your agent class, normally in an agent-based simulation, that will be where you do most of your interesting stuff, because it's the agents and their behavior that you're interested in. So if you want to add more behavior, you just add another method. But of course, I had a number of questions from people saying, well, how are these methods getting called? How does it know when to call this stuff? So we'll now move on to the rest of the stuff, looking at the model and setting up the model class. And this is basically going to control everything else. Okay. So we've written our agent class. Now we're going to write the model class. And the model class is basically going to control the agents, it'll control the environment, and it'll control how the model works via its what's called the schedule. So again, because we're writing object-oriented code, we need to specify the constructor, the init method first. And in the init method, we're going to need to set up the number of agents that we want, the grid that they'll live in, a schedule to determine the order in which agents act in each time step, and that schedule will be the thing that calls the step method that you've just written, and that in turn will call its own behavior methods, like moving and infecting. And we also need to work out the starting cells for the agents, where they're going to start. Okay. Quick question: can anybody think why the schedule might be important, particularly for this? So remember, the schedule is determining the order in which agents act. Why might that be important for this particular model?
Is it something to do with if they're currently in a phase with somebody and they're in, or sorry, in an empty phase, they infect, but there's nobody there to infect, and then they move into the phase with somebody else. So would it
Yes.
Otherwise simulate the infection dying out incorrectly?
Yeah, absolutely. So the order matters here, because basically the schedule is going to determine the order in which agents behave, the order in which agents sort of call their step function, if you like. And their step function will tell them to move with a random probability, and then if they're infected, to infect other people. So imagine you've got an agent in one cell, and then an agent in a neighboring cell, and one of those agents is infected. And if the infected agent were to move first, and they moved into the cell of the uninfected agent, there's a possibility that agent gets infected. But if the other agent were to move first, they could move away so that that agent can't infect them. So the order is going to matter here. And particularly when you're dealing with some sort of infection model, or anything where you're passing on and interacting in that way, the schedule will be important, because that will determine the order in which things happen. So let's have a look now at the model class. So we're going to set up the model class. I've called it disease model, and I've passed in, as I did with the agent up here, where I passed in the agent class that I imported from MESA. So we inherit all the agent stuff. Here, I'm passing in the model class that I've inherited, so I don't need to describe what a MESA model is. We'll inherit that. And so this disease model is basically, we're saying it's a type of MESA model. Okay. So what we're going to do here is we're going to set up our constructor. Now, here are the things that we're going to pass into that constructor, okay? So the first thing we're going to pass in, obviously, is self. This, sorry, just before I do that, this little message that you see here, a model of disease spread for training purposes only, which I put in the 3 inverted commas before and after. You'll be familiar with that way of commenting, which allows you to comment on multiple lines. That will get picked up when we come to do this, build the server. That will get picked up and it'll run as a title on that thing. So we can put in a message that we want for the user at that point. It'll automatically pick that up, whatever we write there. So in the constructor, we're going to pass in self. We're going to pass in something called n. N is basically just the number of agents that we want at the start of the model. Then we're going to pass in a width and height. So that's just the number of cells wide and the number of cells high in our environment. Then we're going to pass these 4 things that you'll be familiar with from the agent class, which is the initial infection, the transmissibility, the level of movement, and the mean length of the disease. Those are the 4 things that will pass into model, and model will then in turn pass that on to the agents when it sets them up. Now, obviously, in this model, all of the agents will have the same infection probability, initial infection probability, the same transmissibility, the same level of movement probability, but you might, so that's why we're passing them in here, and it'll just pass them in turn onto the agents. But of course, in reality, you might have it so that was randomly determined. So you might have, or you might have some other complex setup where different types of agent had different levels of transmissibility, for example, or different levels of movement. If you're modeling older people, for example, you might have a lower level of movement. You could do stuff like that. You can do whatever you like. But just for the purposes of this, we're just going to assume that all of the agents have the same probabilities of moving and infecting and being infected, etc. So we pass them all in here because we're going to in turn the model, whenever it creates a new agent, it'll pass that information across. The first thing we need to do in our constructor here is to set up something called self.running, which is an attribute of the disease model that we set to true. Don't worry about why you have to do that. It's something that's needed for something known as the batch runner, which we'll come on to this afternoon, which allows you basically to run things in batch. You literally just always put that piece of code in, and that'll always work. Okay, so it's just something the batch runner needs. Then we're going to set up the number of agents. I've just called it num agents, and I've set that to n, the number I passed in. That's the number of agents at the start of the model. Obviously, in our model, we're not creating any new agents. The number of agents at the start will be the same as the number of agents at the end, and also we're not modeling death here, but you can remove agents from a model as well as adding agents to a model. But we're not doing that. So that number of agents, we've got 20 agents in the model. There'll be 20 agents at the start and at the end. The next thing we're going to do is set up the grid, and we're going to set up a toroidal multigrid. Now, remember we said that a multigrid is the thing we imported up here, and that just basically means it's a type of grid where we can have more than one agent per cell, which we need here because we need infection to happen, and infection only happens if they're in the same place. The toroidal bit is basically just means that if an agent is on the edge of the grid, say they're on the right-hand side and they move right, they'll appear on the left. Okay, now you don't always want that. So if you don't want a toroidal grid, then you set this third attribute here to false. I can't remember if it defaults to false, actually. I think it may, but it's probably better to put it in so it's clear. But if you put that to false, then if they're on the right, then on the right-hand side of the grid, they won't be able to move right. They'll only be able to move to the cells around them. So a toroidal, think of Pac-Man, basically. You disappear off the right and you come out on the left. And the same if you disappear off the top, you come out at the bottom. Okay. So it may not be that you want that. And for this, we're doing it to demonstrate it. But in reality, you probably, if you were modeling using your grid to represent, let's say, one of the ideas that came up in the cellular automaton session was modeling a classroom, for example. And as far as I know, children who walk out the door on one side don't then magically appear through the window on the left side. And maybe they do. So you probably don't want to use that, depending on what your grid represents. But for the purposes of this, we'll do that just to have people moving about more. So all we do here is we set up the grid. We say it's a multi-grid. That's the thing we imported. And it's got that width and height that we've passed in. when we set up the model, we'll tell it how many cells wide and high we want it, and we're going to have it toroidal. Then we're going to set up the schedule. So this is the scheduler that will determine the order in which agents are being activated. Remember, we just said that's really important, because if somebody moves before somebody can move into their cell and infect them, then that's going to make a difference. Now, for the purposes of this, we're just going to assume that that order is random. So although it matters, we're just going to assume a random order, because we don't have any other information for this particular model about who would move first. Okay, but if you were doing this in reality, you might think about one of the things you think about when you're designing this is, do I have information about who would move first, or the order in which agents would move? Depends what your agents represent, what your model represents, etc. And so if you do have information, you could then set up a schedule to say these people move first, for example. But the random activation here, essentially, it's just everybody's got the same. We don't have any better information, so essentially the chances of that person moving first are the same as that person moving first. It's all random. We don't know any better, and that's going to be okay for this. So we set up the schedule. We say it's a random activation schedule, which we imported. Remember at the top, we imported one of those. So we say, yeah, we want one of those, a random activation schedule, and just pass in self, a copy of this model. Okay. So we've set up the number of agents, the grid, and the scheduler. And now all we need to do is to create the agents at the start of the model. So we're going to do that just very simply in a for loop. Okay, so we'll just say for I in range self.number of agents. So if we've got 20 agents that we've passed in that we're setting up, then it'll do this 20 times. The first thing it's going to do is create the agent. So remember, this is object-oriented programming. So it'll create an instance of this class that we've written up here, the person agent class. I'm just going to call it A. So that will create an agent. And remember, the things that need to be passed into that agent are, ignoring self, we need to pass in a unique ID. We need to pass in model, the model in which they'll live, the initial infection, transmissibility, level of movement, and the mean length of the disease. So that's what we're going to do when we create the agent. So I is the ID, and I'm just going to use an ID because remember it needs one of those. I'm just going to use the ID that's taken from the loop. So the first time around, the first agent will have an ID of 0, then it'll have an ID of 1, then 2, etc. You could do something more fancy if you wanted to. Now, you may be wondering what the self is here. Remember, the second thing it needs to be passed in is the model when you create an agent. Now, the model that needs to be passed in, remember here, we're in the model. This is the model. So when this gets called, when you create a new model, a new instance of the model class, you're essentially saying, pass me in. So pass me to that agent. I'm the model. I need to be passed over to the agent. That's the model that the agent will live in. It's me. Okay. So self always refers to me, and that's a good way to think about self. And then we just pass across these things that, remember, we said these 4 things that we're just going to pass straight across to the agent, because in our model, they're all going to have the same probabilities. Obviously, you may do it differently depending on what you're doing. But in this case, we just, when we create the model, we'll say, here are those 4 parameters, and pass those on to the agent when you create a new one. So that creates a new agent. And then all we then need to do is to add that agent to the schedule. So remember, we've created a schedule up here. We've created a random activation schedule, which basically means they'll act in a random order, and MESA will deal with that for us. And what the schedule's doing, it's basically calling the step method. So it decides which agent is going to act next, and then it'll call the step method for that agent. And all of the agents, even though it's random, in a time unit, it'll make sure all agents have a chance to act. It's just the order in which they act will be random. So adds that agent to the schedule. That's all technically we need to do, but what we also want to do here down here is to add, we need to add the agent to a cell to start them off in our environment. And what I've decided to do here, what I'm going to try and do to try and spread my agents out as much as possible at the start, is to add the agent that we create to a random empty cell. Okay, so I don't have to do this. I've just made that decision for my particular model to say, okay, when I start off the locations of the agents, I want them ideally to be in empty cells where that's possible. So I'm going to use a try except statement. So I'm going to try putting them in an empty cell, and there's a neat little method of the grid where you can find an empty cell, and it's called find empty, and it just finds an empty cell at random. And so I'm going to try doing that. So I'm going to find an empty cell, and I'll make that the start cell, and then I'll just tell using the place agent method of the grid, which needs two things to be passed to it: the agent that you want to place and where you want to place them. So here I'll say, okay, it's this agent that I've just created up here, agent A, and the start cell is whatever one I found randomly here that was empty. The reason I put this in a try except statement is because depending on the number of agents you've got and the size of your grid, there may be no more empty cells left. They may have all, if you've got 100 cells and 108, and you're now creating your 101st agent, all of the previous agents will be occupying cells. So now there are no more empty cells. So this would result in an error because there is no empty cell to find. So that, by putting in a try except statement, will then kick out and go to the except bit. So if we can't find an empty cell for them, then what we'll do in this case, I'm just going to get them to pick any cell at random. So they'll have a cellmate now, but we'll just pick one at random. So all I do here, I'm just going to literally randomly pick an X and Y coordinate. So I'm going to take a value of X that I'm going to randomly, I'll use the rand range method of the random library, which basically just says pick a random number up to this number. Between 0 and this number, so this will give it between 0 and whatever the width is, and a random number between 0 and whatever the height is. So that'll be my X and Y coordinate, and then place the agent, use the same method I used up here to place the agent at that particular coordinate. So the cells are defined in terms of their coordinates, the X and Y coordinates. Okay, so try finding an empty cell, but if that doesn't work, if there are no more empty cells, then just pick a cell at random, basically. Okay, so that's the constructor. That's all we've had to do. We've just set up the number of agents that we want. We set up the grid that we want, which in our case is going to be a multi-grid, which allows multiple agents per cell. We've set up the scheduler that we want that will control the order in which the agents act. We're just having a random scheduler, random activation scheduler, and then we'll start creating our agents at the start of the model. And we're just going to keep creating them in a for loop. We'll pass over the information they need. We'll pass them a copy of myself as the model. That's they're going to live in me. We'll add them to the schedule, and then we'll try putting them in an empty cell. And if we can't find an empty cell, we'll just put them somewhere randomly. Okay. And so every time, so when we create an instance of the model, that's what it'll do. It'll go through all that stuff. Okay, so what we then need to do, the only other thing we need to do for the model is to define the step function. So like the agent had a step function, which defines the order in which things happen, the model also has a step function. But here, it's really easy. All we need to tell the model to do in its step function is to step forward the schedule, i.e. to activate, what the scheduler will do is it'll activate the step function for each agent, and it'll do that in the order in which we defined, which we've said it's a random activation scheduler. So it'll just randomly, it'll make sure they all have a chance to act in that time step, but the order in which they do it will be random. So it'll just call the step method for each agent that it's got. And then when it's finished, it'll just move on to the next time step. So all we're doing here in our model step method is just telling it to advance the model by one step. So self.schedule.step, and then it'll basically do all that magic for you. So you create the model here, and then at each step, it'll basically say, move the scheduler on, and the scheduler is doing all the hard work for you. It's sorting out when the agents interact and when they act and where they move and all that kind of stuff. It's doing all that based on what you've defined up here. So it'll just call the step method of each agent. And remember, we've defined the step method, and the step method tells it that the agent might move. And then if it does, it needs to move and call this move method that we've written. And then it might infect other people, and then it'll call the infect method. So that's the order in which it does things. Okay. And that's it. That's the model file. We've written the model. That's it. That's all we've done. And hopefully you can see that's actually pretty easy. we've created a disease model that has all this behavior, but because we're using MESA, we don't need to set up, and this is what a grid looks like, and this is and how now I'm going to write to the scheduler, which determines the order in which they, because we've already got concepts of that, we import them, so we can use that stuff and then just define what we want for our particular model. And that's the, much like SymPy, that's the advantage where we didn't have to, you know, define what a discrete event simulation was from scratch. Here we don't need to define what an agent-based simulation is. It knows what it is, and we just tell it the how we want what type of grid we want and how we want our agents to be selected and things like that. So that's it. That's the model. It's done. The next thing we need to do is to do the disease run .py. Remember, we said that we need 3 modules, or we need at least 2, and this is the second compulsory one. And the disease run module will basically control how the model runs, and you can run it either as a single run, or you can run it as a batch run, where you run it lots of times and take results over a batch, like we did with SymPy. Or we can use a server to visualize the model, so we can watch it run live, and we can watch the agents moving about and getting infected and stuff like that. We can watch all that, and it's really cool. So we're going to, initially, we're going to run it using the last of these options. We're going to set up a server so that we can watch this thing run live. Okay. Now, when you were doing this in reality, you'd probably want to have it so that you can demo it like that. But then if you're actually getting results, you'd use a batch run as you would for discrete event simulation. And then you could just change the run file. And I'll show you how to do that later. And we'll come on to how you do batch runs. It's really easy in MESA. But for now, we're going to set it up so it just runs a single run of the model, and we can watch it. We can watch it play out and people moving around. Unfortunately, that makes the writing of the run file really, really easy, because all we need to do in the run file is to tell it to launch a server. And so what we do, if I cancel out that. So if we look at the run file here, those 3 lines of code, you just copy and paste them, and that's your run file. That's it. So all we're doing, just to explain, it's we're importing from disease server, which is the module we're about to write over here. That's the one we're going to come on to in a second. So from that, import the server, which again is going to be part of the thing we write. We set up a server port, which is 8521, which is the default. You always use that. And then, unless you were doing anything fancy, putting this on a separate server or something like that. And then you just tell it to launch. That's it. So those 3 lines of code, don't worry about them. Just copy and paste them. That's your run file. That's all you need to do. If you're doing anything, as I say, more fancy by putting this stuff up on a server, but then if you're doing that, you'll know about the server ports that you'll need, and because you'll already be exploring that. But if you're just running this yourself and showing other people which most of you will be doing for your projects, this is all you need to do. Okay. Now, one thing to flag up here, because essentially what you're doing is you're opening a port on your computer, and what's going to happen is that it'll set up a little server on your computer, and you'll connect into that server. So much like when you connect to the internet, you're connecting to servers somewhere else in the world, and then you're connecting into that. Here, you're going to be doing the same thing. It's just that the server is going to run on your own computer, and that server will show you that will run the model and show you the visualization of it. Okay. Some of you may have issues with this, because it may be that your IT department has blocked something in terms of opening up server ports. We did have a few instances of that last year. So as I say, if you do run into that problem and it doesn't work, don't worry, because in reality, this is optional anyway. But B, I'm sure there will be somebody in your group that will be able to do this. Most people seem to be okay with it last year. There was just a couple where they'd really locked things down. If that is the case, you do get locked down, it may be worth speaking to your IT department and see if they can unblock that for you. I don't know whether they will. Well, you can have that conversation. But that's the run file. Okay, so that's all you need to do for that. So then we come on to the third provider file, which we only need this one if we're going to do it using a server. So we're going to write this third file, and it's going to be called diseaseserver.py. So the first thing we're going to do is we're going to import the libraries that we need, as ever with Python. So here are the four things we're going to import. The first thing we're going to import is the thing we've just written, the disease model.py. From that, from disease model, we're going to import the disease model class, the one we just wrote down here. We don't need to import the agents because the disease server just needs the model. The disease model class will sort out everything else. We just need to import this bit because that's the bit we're going to need to start up a new model and get it to interact with the server. So we're going to import from this is probably the first instance you had where you've written something and then you import it. So you've written your own module and you import it somewhere else. Then we're going to import a few other things. So we're going to import from MESA.visualizations.module something called a canvas grid. This is basically just the grid that will show on the web browser. We're also going to import from MESA.visualization.modular visualization a modular server. That's basically the server that's going to run this, that's going to host our visualization. And we're also going to import here from MESA.visualization.userParam something called a user settable parameter. This class is really useful because it allows us to put in things like sliders really easy, so that we can have the user play around with the model, so the user can then change the level of transmissibility or the probability of movement and things like that, and just have a little slider that neatly does that, and it's really good for that. Okay, so that's what we're going to import. We're going to import the model that we've just written, as well as these things that we need for the server, which is a canvas grid, which will display it, the server, which will run it, and this user settable parameter thing, because I want to put in some nice sliders, basically. So next we need to write something called a portrayal function, which is just basically a fancy way of saying when you draw agents, telling the server when you draw agents on the grid, this is how I want them to be drawn. This is how I want them to be portrayed. Okay, so what we're going to do, we're just going to have a really simple visualization to say that when you draw agents, I want them to be represented as filled circles with a radius of 0.5, and they're colored red if they're infected, and if they're not infected, they're small and gray. So I'll have big red circles for infected agents and small gray ones for uninfected agents. So we'll be able to really easily see the infected people because there'll be big red circles, basically. And the layer value that we'll set up will determine which ones should go on top if you've got more than one in a cell. So a higher value that will get a priority. So let's have a look at the portrayal function. So I'm going to set up the agent portrayal function here. I've got agent portrayal. I pass in an agent because it's an agent object. This is basically when the server does this, it'll pass across an agent to be drawn. And so this is one of our agents that will need to be passed in. So I'm going to set up what's known as a portrayal dictionary here, and that'll set up the key aspects of our portrayal. Okay, so you're used to seeing dictionaries. I've just called it portrayal. I'm going to set up that I want the shape to be a circle, so I want them drawn as circles. I want filled to be true because I want them to be filled circles, and I want the default radius to be 0.5. Okay, you can play around with these things, and if you look at the MESA documentation, it'll tell you all the different things you can do in terms of different shapes and all the different options you can have. But for here, we're just going to have some simple circles that are filled in, basically. So then I'm going to specify, so that's the default visualization, but then I'm going to specify how I want agents drawn differently depending on their characteristics. And the key thing here is that I want agents drawn differently depending on if they're infected or not. So you could, this is just an attribute of the agent, so you could have different visualizations for agents as well, depending on how long their disease duration is. So as they get better, maybe the color changes or the shape changes or something like that. So you could easily do that, and you just change it here. You just look at the disease duration, and you have different colors or shapes. So here we're saying if the agent is infected, so if the agent that you're drawing, if their infected attribute is true, then change the portrayal value that I've set, the color value in the Portrayal Dictionary, which we haven't set up here, but is part of the Portrayal Dictionary. Again, the MESA documentation shows you all the different options you can have. I want the color in the Portrayal Dictionary to be red. So if they're infected, I want them to be red, and I want the layer value to be 0. So they get a lower priority because they're going to be bigger. So they'll go down towards the bottom. But everything else will be drawn as this. So if an agent's infected, they'll be red, they'll be at the bottom, and they'll also inherit all this stuff. There'll be a circle which will be filled and it'll have a radius of 0.5. If they're not infected, then I want the color to be gray. And I'm going to put a layer of layer value 1, so that's higher than 0. So that means if they're in the same cell as an infected one, they'll go on top. And I want I'm going to change something that I've changed that I set up as the default up here. I'm going to make them smaller. So I've changed the radius to 0.2. So essentially, if you've got an infected and an uninfected agent in the same cell, you should see a big red circle at the bottom, which will be your infected agent, and a small gray circle on the top, which will be an uninfected agent. Okay. So that's setting up the portrayal. We set up the kind of default values and then more unique values depending on how we want specific agents to be drawn, depending on their particular attributes, which is I've just done it based on whether they're infected or not. As I say, you could put in whatever you like here. But that's probably the thing we're most interested in for an infection model. Then the last thing we need to do is we just return the portrayal. And this, so the Portrayal Dictionary basically, and this will then return that so that when the server draws an agent, it tells them how to draw it. So the server will call this method basically every time it needs to draw an agent, and it'll tell them how to draw it. Okay, so that's the portrayal function. Now we need to set up the elements that are going to make up our visualization. So for now, we're going to add some bits in later, but for now, we're just going to set up one visualization element. We're just going to have a grid that contains the elements that are going to be portrayed or drawn in the manner that we've just specified in the portrayal function. And we're going to set up this grid so that it's got 10 by 10 cells and it's 500 by 500 pixels when it's drawn on the screen. Okay, so here's how we do it here. We just set up a grid. We say it's a canvas grid. Remember, we imported one of those up here. And we pass in the agent portrayal. That's this method that we've, this function that we've written up here. So that's the function. That's how we want you to draw agents. And then it needs to know how many cells wide and high, so 10 by 10, and how many pixels wide and high. So I've done a 500 by 500. You can play around with this. If you wanted a 20 by 20 grid, you could do that and have the different pixel size and however you want to do that. Okay, so we're just setting up a grid here. We will add more visualization elements later, but at the moment we're just going to have a grid that's drawn, and that grid will show us where our agents are and how they're moving around. So then we're going to set up the user interface. Now, I mentioned before that MESA allows us to really easily add a user interface that allows the user to play around with different parameter values and have little sliders and stuff like that. And it's really good for stuff like that. You can do it really easily. So that's what we're going to put in here. We're going to have 5 sliders so that the user can play with these 5 things. I'm going to set up so they can change the number of agents in the model. They can change the probability that an agent's infected at the start of the model. They can change the transmissibility of the disease, i.e. the probability that they infect someone else if they're infected. The level of movement, which remember is the probability that an agent moves at any time step. And the mean length of the disease in days, which is our time unit. So the user can play around with this. We'll have default values, but the user can play around with that and see what happens when they increase the number of agents or they increase the level of movement, etc. So what we need to do for each user settable parameter that we want, we need to specify the type. We're just going to have sliders, but there are different types, and as I say, the MESA documentation will tell you about those. But we're just going to have some sliders. We need to say the text that we want for the label on that slider, the default value, min, max, and increments. Let's have a look at that code. So here's where I'm going to set it up. So I've set up my 5 sliders separately. So let's just look at the first one. So I've called this the number of agents slider. So this is going to be the slider that they can use to change the number of agents that are in the model. And I set that up as an instance of the user settable parameter class, which remember I imported at the top. So it's one of those, and it needs these 6 pieces of information. It needs to know what type of user settable parameter it is. And as I say, they're just going to be all sliders here. So I say it's a slider I want. I want this to be the text next to that slider. So that'll explain to the user what the slider's doing. And then this third value here, that's going to be the default value. So by default, it'll default to having 20 agents in the model. That's what it'll start at on that slider. Then I specify the minimum and the maximum value. So I'm going to allow the user to go down to 2 agents. There's no point in allowing them to go down to 1 agent. An infection model only has 1 person in it. It's a pretty boring infection model. So we want a minimum of 2, and I'm going to let them have up to 100 agents. And obviously you can have whatever you like. And this last one basically says the increment. So how much, whenever they slide the slider, what's the increment? So they can change it by an increment of 1. So they can have any value between 2 and 100 in increments of 1. Then I do the same thing here for my initial infection. That's the probability that they're initially infected when a new agent's created. At the start of the model, again, that's a slider. Here's my text. And this one's going to default to a probability of 0.3. So at the start of the model, there's a 30% chance that an agent will be infected. So about 30% of our agents at the start should be infected. I'm going to have a minimum value of 0.01, a maximum value of 1, because obviously you can't have more than 1 for a probability. And the increment here will be 0.01. So they can change that in increments of 0.01 between 0.01 and 1. Okay. And then I just do that for all of the ones I want: the transmissibility, the level of movement, mean length of disease, etc. And that will set up my 5 sliders. So then the only other thing that I then need to do is to set up my server as a modular server. This is the server that's going to be launched by the run file. So the run file, we told it to launch a server. If we go back to the run file, we said server.launch. That's the server that we're talking about. That's the one we need to set up. Because up here, we said from disease server, this thing we're writing now, import server. That's what we're about to write. We'll give it, tell it the port that it needs to open, and then we'll tell it to launch. So this is the server we're now setting up. So we're going to set that up as a modular server. Remember, we imported that at the top. We imported the modular server class. So we're saying the server we want is this modular server one. That's the one you'll always want for this. And then we need to pass in these pieces of information. We need to pass in the model that the server is going to run. Remember, that's the disease model that we imported up here that we wrote over here. Okay, so that's the model class that we've imported. That's the model that we want our server to run. Then we need to pass in the list of elements that we want the server to visualize. Now, we've only got one element at the moment that we wanted to visualize. That's a grid. Okay, that will show, and we'll add more later. But you still have to pass that as a list. It's expecting it as a list. So even if you've only got one element, you need to have that as a list. So I've just got a list with grid, which is the grid I set up here, which I said is going to use this portrayal method to draw our agents. It's going to be 10 by 10 cells, and it's going to be 500 by 500 pixels. So that's the list of elements that we want it to draw. Then I'm going to give a title to display for the server visualizations. This will be the title. Remember the thing back here in the disease model, that will be a sort of subtitle. You'll see it when it runs. And then I'm going to pass in this dictionary, which will basically link the user interface elements that I set up here to the values in our model, because here all we've done is we've set up some sliders, but we need to link the values on those sliders to the model so it changes the numbers in our model. Okay, so here we're going to set up a dictionary. Now the values in the inverted commas, so your key values here, the lookup values in your dictionary, that you put in inverted commas, they must match the respective variable name in the model class. So remember, number of agents, when we set up a new model, that gets passed in as n. That has to be passed in. So whatever you pass in this constructor, whatever name you use here in this bit, that's the name you have to use, not this bit. So this is why I've deliberately set up num agents as the attribute in the model class to be a different name to show this. You have to give this name, the name that you use when you pass it in, the name's expecting when it gets passed in. That's the way you link it. Okay, so I'm going to say n, that grab that value from the number of agents slider that I've set up here. I'll come back to these two. Grab the initial infection, which again, if we go back to here, initial infection is expecting that name, which will set up the probability that they're initially infected. Grab that from the initial infection slider up here, and so on for all of them. The width and height is just basically where we set up the width and height of the grid, and I've just hard-coded those to be 10. Obviously, that needs to match what you set up as the grid up here, otherwise you're going to get well, it doesn't have to, although I've not tried what would happen, but you obviously want the grid that you draw to be the same size as the grid that your model is using. So in reality, you probably want to set up a grid width and height separate variables and use the same values here and here, just to avoid that problem. Okay, so that's all it does. So the server, we just say we want a modular server. It's going to use this model class that we wrote in the disease model. We want it to draw these things, which is just a grid. And we want it to be called the disease spread model as the title. And I'm going to pass this dictionary, which says link these sliders that I set up here to these values in my model. Okay. So let's run it. Let's see what happens. Okay, so we should now have a working model. We've built it. We've written our disease model file, which has all the interesting stuff in it. The disease run file, which was just three lines of code telling it to run the server, and the server file, which we've just written, which tells it to launch the server, so we can watch all this happen. So what I want you to do, I'll start it running here, so you can just see it going. Actually, before I do that, there's a few things you need to know. So I'm going to put you into your groups in a minute to have a play around with this. And I want you to play around with the different sliders and see how things change. A few things to note. If you change the sliders, you have to click reset at the top of the model to reset and kick in those new values. So if you change the number of agents, you need to click reset. It'll then reset the model with that new value you've selected. Also importantly, if you close the model, i.e. you close your browser and then you want to launch it again, you'll have to restart your kernel in Spider. Otherwise, the port will be blocked because it keeps the port open, but you haven't told it to close. So remember, I think you're all used to restarting the kernel by now. But if you're not, just remember, just go into your IPython console here, click on the three little horizontal lines and click restart kernel, and that will flush it. It'll flush your port. Now, and the third thing, obviously, it's possible you may have problems with this, as I mentioned earlier. So if it doesn't work, find someone in your group where it does work. I'm hoping most of you will be able to run this, but I do strongly suspect that a few of you may get issues, because if your IT has locked things down in terms of server ports, networking ports, sorry, you may have a problem. So we'll soon see. We'll see what happens. But let me run it so you can at least see it. The way you do it is you need to go into the disease run file, this one, and you need to run from this. Don't run that and don't run that. You run this one, okay? Because the disease run file will run this disease server, which in turn will run the disease model, which in turn will start creating your agents, etc. So it all starts from the disease run. So fingers crossed, it should work on mine, but let's push F5. And you'll see it'll give a web address, an IP address that it's launching at. It should launch my browser, and here we go. So this is the disease spread model. That's the title that I specified when I specified the server. And if I click on the About button, that's the little message that we put in the comment bit in the disease model. So you can see we've got our agents. We've got our red agents, so those are infected, and we've got our grey agents that are uninfected. And if we hover over the grey ones, you can see that they it says layer 1. Remember, we specified that they appear on top. So it specifies that when you hover over it. You can specify the number of frames per second. It puts that in automatically, so you can have it run faster or slower. And I've got all my sliders here, so I can play around with things. So I'm just going to leave it at the defaults for now. And I can just click, so I can click start, which will just play it running. I can click step, where every time you click step, it'll move on one time step. And I can click reset if I want to reset and go back to the start, and it'll randomly generate another load of agents, and it'll be based on your sliders. So if you change your sliders, remember you need to click reset, and then it'll kick those values in. So let's click start, see what happens. There we go. So we can see our agents moving around. and we've still got an infected agent there. He's moving around. Oh, is he going to infect anyone else? No, and the disease has died out. Okay, but so I click stop. Let's increase the level of transmissibility. I'll click reset, see what happens. Right, so we're not dying out so quickly now because the disease now is more transmissible. Oh, we have one pop up there. No, and it still died out, and we can see when it died out as well. So what I want you to do is I'm going to put you into your groups, have a play around with this for about 15 minutes, just have get a feel for this, have an explore of how this model works, try different things, and we'll come back at about 5:02. Okay. Any questions about any of that? Sorry. No, good. Okay. Have a play, have a bit of fun, and we'll come back at 5:02. Let me open up the groups. Okay, right. So hopefully you all had a chance to have a little play around with that. I saw a lot of you using it, so that's a good sign. I know the few people who drew the short straw and it's not working, but hopefully I think it looks like most of you are able to get something running, which is good. As I say, it's not essential to do this, but it certainly from a if you were presenting, showing this model to people, engaging with stakeholders, doing this for a project, it's a really nice way to be able to show people how the model works, because they can see a very clear visualization of it. So it's very powerful from that sense. Okay, let's plow on. Where are we here? Right. So, oops. That's not worked. Try again. There we go. So let's talk about data collectors. So remember, we imported this thing called a data collector right at the very start, which we haven't yet used. The reason we've done that is because it would be really useful to collect data throughout the run of the model, so we could, collect our results or display the output to a graph or whatever we might want to do, because we're probably going to want to use this, if we're doing this for real, to generate some insight about something, to answer some sort of question. So as with SymPy, we want to be able to collect results, and I think MESA does this much more elegantly than SymPy does, actually. So MESA, we can use this using the data collectors class. So we imported the data collector class at the start of the disease model.py file, and now we're going to use it. So what we're going to do is we're going to set up a data collector that will monitor the total number of infected agents over time. So we can monitor how the number of people who are infected changes over time in our model, depending on what transmissibility we specify, level of movement, etc. And the first thing we're going to do is we need to write a function that will calculate the result that we want to collect. So in this case, that's the total number of agents who are infected, and we're going to write that in the disease model module. So in the disease model.py file. And we're going to do that as a standalone function in the module. It's not part of one of the classes. It's not part of the person agent class. It's not part of the disease model class. It's just part of that disease model.py file. Now, I keep using the word we there, and I'm not quite sure why, because I'm going to get you to do it. So I want you to work in your groups. I'm going to get you to write this function. So you're going to write a function called calculate number infected in the disease model.py file. Remember, it's a standalone function, so it shouldn't be part of the classes. You've got two class definitions. It's not part of those. It's just a standalone function. What the function needs to do is to accept a single input of a MESA model object. I'd recommend, you can call it whatever you like, but I'd recommend just calling it model, as we have elsewhere. It sets up a counter that will keep count of the total number of infected agents in the model over time, which should default to 0. It'll set up a list of agents in the MESA model that can be obtained by accessing schedule.agents on the on the model object. So the model object will have, you can access something called model.schedule.agents, and that will give you a list of agents that are in that model. What I want you to do is use a list comprehension to generate a new list from that list, which contains the Boolean infected attribute of each agent in that schedule. Then I want you to loop through your new list to count up how many infected agents there are, and update the counter that you set up at the start of the function, and then return that number as an output from the function. So basically what you're doing, that sounds more convoluted than it is because I'm spelling it out for you step by step. Basically what you're going to do, you're going to set up a new function that you pass in a MESA model. You set this counter, set up this counter, it starts at 0, and then you basically grab the number, a list of the agents that you've got on the model. You look through each of those agents to see if they're infected or not, and then everyone that's infected, you look through that list and you generate a new list of those agents who are infected, and then you loop through that list to count up how many infected agents there are and update the counter. Okay, now I've given you 30 minutes, which will take you to the end of the session, end of this morning's bit. You probably won't need that, so I'll keep an eye on things. I may call you back a little bit sooner because we're a tiny bit behind. That's okay, because I've got buffers built into today. So I'll see how you get on. So I'll put you into your groups now. Don't overthink it, just follow the instructions there. And it's not overly complex what I'm asking you to write. So if you're thinking very complex, you've probably gone in the wrong direction. So have a go at that. Just follow the instructions there. But remember, this is you need to write this in the disease model.py file, and it shouldn't be part of the classes. So it's a standalone function. So just to flag up in your repository, you should have a folder called disease model. That's the one you need. Okay, that's the one you need to open. You need to open these 3 here. Okay, so open those 3 files, and it's the disease model.py that you need to deal with. So I'd close down anything else that you're using, because otherwise you'll end up with lots of different files called the same thing. So it's this set here that you need to use. Okay, let's stop sharing and I'll put you in your groups. Hi everyone. Sorry, I thought I'd put you back. So I bounced around to quite a few of the groups, and I think you were done. And I did think you'd probably be done quite quickly. Don't worry if you didn't quite get there. I'm going to quickly rattle through the solution now anyway. But I think you probably did in most cases. So let me just share my screen. Okay, so all we're asking you to do here is basically to set this up. This calculate number infected function, which we put separate in the disease model.py file just as its own standalone thing, and it's so that we can it can be used and referenced separately without creating a model or an agent. So we pass in a model because it needs to have a model to run on, and all I'm going to do is set up a counter. I've called mine total infected. Then I'm going to use a list comprehension to grab a new list, which basically just contains lots of true and false values, indicating whether each agent's infected or not. So I use my list comprehension to say, and again, we'll read it from the middle, from the for statement. It makes it easier. For each agent in the model.schedule.agents, which is where the list of agents is kept, then give me back the agent.infected attribute, so whether they're infected or not. And it'll put that in this list. Now, what I can then do is just then loop through that list using a simple for loop and see if each value is true. And if it is true, I'll add 1 to my counter, then I return it. Now, there are simpler ways to do that. So I deliberately got you to do it sort of longhand, mainly to just get you used to using list comprehensions and using for loops and incrementing. So it's just to flex your Python muscles, really, more than anything. But of course, there are simpler ways. I mean, what you could have done, for example, I saw somebody do it in a single line of code. You could also just here, you could just say, you could add a conditional logic onto your list comprehension to say only grab me back ones where the infected attribute is true, and therefore then just take the length of that list will give you that as well. So there's lots of ways to do it, but the key thing, you need to count up how many trues there are against infected in your agents. So however you want to do that will work. Okay, so that's kind of the first step for setting up the data collector. There we go. Next, what we need to do is right, isn't it? Yes. Next, what we need to do is set up the data collector, and we specify the function that we've just written as one of the what we call model reporters. And you can have agent reporters as well, but you'll mostly be using model reporters. Basically, what we do in the disease model class at the very end of the constructor for the disease model, we insert the following code. So let's flip over to the code. Disease model. So this is our disease model class. Here's our constructor. And at the end of the constructor, after we've set up the all our agents, created all our agents, we're going to create a new data collector. So we create a new data collector and we're going to pass in a model reporter. And that's basically this function. We say this, a model reporter. We've written a function which tells you how to report. This is one of the things we want to report on. So we set up a model reporter and we specify it as a dictionary. And we specify the key value pair here. The index value, which is total infected, is the name of the result that we want, and we need to make sure that that's consistent when we use it elsewhere. So that will be the name of the result that we'll need to reference. And the value against that key is the name of the method that we want it to use, which is the one we just wrote down here, calculate number of infected. So if you called that Bob Jones, you'd put Bob Jones in here. It's whatever you've called your method that will calculate it. So you're saying, this is what I want to call that result, and this is the method I want you to use that will calculate that result. Okay, we haven't got any, don't worry about the agent reporters for this. Most of the stuff you'll be doing is model reporters anyway. So that will set up a data collector against that model. So then the model will have its own data collector and it'll be based on this stuff. Oops. So we also need to tell the model that we want to collect data from the data collector at each step of the model, because we've set one up and we've told it the function we want to use to calculate the result we want, which in this case is total number of infected at any one time. But we also need to tell it to actually collect the data. So the way we do that is we use, again, in the disease model class, we go into the step function. So before we just had one line of code in here that just told the model to step forward the scheduler. We're just going to add an extra line of code here in the model step function that basically just tells the data collector to collect. Now, the data collector can have multiple reporters. So as we collect more, we may have different things that we want to monitor over time. If you had, for example, a vaccination model in here, you might want to look at the number of vaccinated over time as well as the total number of infected. And they can all be stored in the same data collector. They'll just have different model reporters. And you'll see an example. I've put in some, I'll share some code where I've put in a vaccination model into this and you can see how that works. So all we need to do in here is to refer to this data collector. Remember, the data collector is stored against self because it's now an attribute of the model because we set it up to be self.datacollector. So grab my data collector and tell it to collect, and the thing it needs to pass in is me I'm the model, because remember what this data collector will do. It will call this function that we wrote down here, and we need to pass in the model. It needs to know what model to run this on, so we pass in self. Okay, so that's all we do. So we've set up a method that will calculate the results. Then we set up a data collector in the constructor. So when we create a new model, this data collector will be instantiated as well. And then we tell it at each step of the model to collect the results. And that means that it'll run this run this function every time that we have a time step in the model. And that will give us the number of infected over time. So we don't just run it once. You may only want it once, maybe at the end of the model, but that's unlikely. You're probably going to want to monitor it over time for something like this. So this will say at each step, run this so I can monitor the number of infected over time. So now we've got the model collecting the number of infected people over time. All we need to do is decide how to output this. And we could just, write the results out to file. That'd be pretty boring, wouldn't it? And we've got a server here. So why don't we get the server to draw a nice fancy graph that shows the total number of infected people over time as the model runs? Unfortunately, MESA's got some really nice graph visualizations built into it as well. So let's do it. So we need to go back to the disease server file to do this. We're going to do three things. First, we're going to add what's known as a chart module. We're going to import one of those. And that's basically going to be used for drawing graphs. So if I go back to the disease server, you can see I've added this import line here, import chart module. Anytime you want to do some graphs in MESA, just import that thing, and this will give us some nice fancy stuff. It's a bit like matplotlib, but for MESA. You could, of course, use matplotlib if you wanted to. You're in Python, but it's got really nice stuff built in. The second thing we're going to do is we're going to specify the graph. We're going to do this under where we specified the grid with grid equals. So remember, in the server here, we set up our visualization elements. We only had one at the time. We had a grid, but now we're also going to set up a graph. So I'm setting up my graph here. I'm going to say that it's a chart module. So it's one of these that I've just imported. So it'll know it's a graph that it needs to draw. I'm going to pass it in a list which contains a dictionary which has the label. So 2 pieces of information here. It's got the label that we want it to draw. Remember, that's total infected. So when we set up the data collector back here, we said that we want you to use this method, and that will be our total infected result. Okay, and we called it that. So whatever you called it here, that's what you need to refer to here. That's the label. That's how it will link the chart that is drawing to the result. So we say a label, and the label is total infected, and you can specify how you want to visualize. I've just specified a color here, but you can do all sorts. So I've just said I want the color of that line to be red. So it'll draw a red line on that graph that for the total number of infected over time. And of course, you may have, if you had vaccination in there, you might have total number of vaccinated over time, and that might be a blue line on the same graph, for example. And I also just need to pass in the name of the data collector that will collect that data. And remember, I just called it data collector. And usually you'd probably only have one data collector that will collect all the stuff, but you might have multiple ones. So you'd need to set them up differently. So that's the second thing. So I've imported my chart module. I've then set up the graph and told it how to link into the result I want. And then the final thing I need to do is just add that graph to the list of things that I wanted to visualize. So when I set up the server, before we just had a list here that just had the word grid in it because it was just going to set up the grid. But I've now got a second thing I want to draw, and it's this thing that I set up here, total infected graph. So I'm just going to add that to that list. Okay. And that's it. That's all I need to do. I've set up the data collector. I've told it how to collect results. I've told it what that result is called, total infected. And then in the server, I can then draw that just by importing the chart module and then setting up a new graph that says, grab me that result. That's the result I want you to plot over time. And I want that to be a red line. And the data collector that does this is called data collector. And then add it to my list of things that I want the server to draw. So let's now quickly run it. Did I leave my other one open? Yes, I did. So I need to close that down. I need to restart my kernel. It shouldn't take a second. There we go. So now I'll start again. I'll run it from diseaserun.py, push F5. And it hasn't worked. I thought that might happen. Okay, let me close that down again. This has happened to me before. And I'm not entirely sure why. It's like it's still using the old one. Let me just push that again. Usually if I do it twice, it works. Let's see. Fingers crossed. There we go. Hey, there you go. So if it doesn't work, if in doubt, just do the same thing again. That's a good rule for life. So we've got exactly the same as before, except we've now also got this graph. So just to make it a bit more interesting, I'm going to put a bit more agents in here, a bit more probability of infection, a bit more transmissibility, get them moving about a bit more, and increase the length of the disease. Maybe not that much. Okay, let's start it running. So as well as being able to monitor up here, we've now got a nice little dynamic graph that's monitoring the total number of infected over time. So we're dropping, got a little peak though coming back up here, but we're seeing them dropping and it's dying out. That's actually died out quite quickly. But that's a really nice little graph that you've been able to do in 3 steps just to track this particular result that you've got. And as I say, you can then add in extra lines to this as well, where you can, if you're monitoring something else, you can monitor that on the same graph, or you can have a different graph and you just set up in exactly the same way. Just have a third visualization element that you put on here as well. Okay, so it's really easy to add that stuff in. And that's it. Crikey, I've actually finished on time. That's miraculous. Okay, so that's it for this morning. So go and have a lunch break now. We'll resume at 1:30. You can stay on the call. Just make sure you're muted. And basically what we're going to do this afternoon, I'm going to show you how to, a few more features of MESA. I can show you how you do batch runs, which is a really useful feature. And you'll see how you not only can run things in batch, but how you can automatically get it to test out different scenarios and different combinations of parameter values. It's a really nice feature that I wish there was in SymPy, because it's really good for doing this kind of stuff. You can say, well, try having 10 agents and with these different parameter values, etc. And it'll do all that automatically for you. So it's really nice. As I'll show you that, and then we're going to spend basically this afternoon, most of this afternoon, being creative. So I'm going to get you in your groups to basically come up with some ideas, or you may choose to use the ideas you came up with in the cellular automaton session, or you may have some new ideas based on what you've seen today. Basically, you're going to design and build your own agent-based simulation using MESA. You're going to build a prototype, and then you're going to demo them to the group. So go and have a break, have a stretch your legs, and go and get something to eat. And then I will see you all at 1:30. Okay, see you there. Okay, good afternoon, everyone. Welcome back for even more agent-based simulation. So what have you let yourselves in for? So this morning, obviously, we showed you how to build the principal components of an agent-based simulation using MESA, and hopefully, what you've been finding with this is actually it's quite friendly. It's quite a nice little package, and actually, you can build the models itself relatively easily, and actually get some really nice server-based visualization as well. Again, relatively easily, and a lot of the stuff that we showed you, obviously the server-based stuff, a lot of that you'll be copying and pasting and just adjusting for your particular needs, and then really the creativity comes in terms of the designing the model and how your agents are going to work and what your grid represents, etc. And that's all kind of stuff that you can build in and you can play around with. But the basic structure of a MESA model is actually I think pretty straightforward, and it's quite nicely done. Hopefully you've seen what I meant when I said earlier about how sort of agent-based simulation and object-oriented programming are kind of made for each other, because they're kind of natural fit, and so this is hopefully helping your object-oriented stuff as well, which, as you probably saw, hopefully you saw on Slack yesterday, the Python assessment will be testing you on aspects of object-oriented programming. It won't go into anything complex. You won't be doing inheritance or anything like that, but just the basics of being able to create classes and creating a constructor and the methods in that. So so this is good practice for you. So if you can get your head around this kind of stuff, this is more than you'd need for the Python assessment. Okay, so let's what we're going to do this afternoon, there's a little extra bit that I want to talk to you about, but then most of the afternoon you're going to spend being creative in your teams, and you're going to design and build your own agent-based simulation. And then I'm going to ask all the teams to present these prototype models at the end, so you're going to get a chance to actually use MESA in earnest. So let's start by talking about batch runs. So obviously, so far, when we've been running our agent-based models, we've been running them live, essentially, with a server visualization, and we've been watching a run through, and that's really useful, and particularly as you're exploring your model, you're building up your model. That's probably how you want to start, and it's also really useful when you come to show your model to your stakeholders, so that you can present what you're doing and show them how it works, and get them to interact and feedback. As part of that, remember, going back to the very first session, we talked about the model design process being an iterative process where you're constantly getting feedback and getting ideas and building those kinds of things in. And so having that kind of visual representation of the model is a really good way in which you can show them what's happening and get them to sort of fire off ideas about what would work and what wouldn't, etc. But when you come to actually generate and want to use your model to get results out for whatever questions you're posing of it, then you probably want to run the model in batch. Much as we do with discrete event simulation, we don't tend to just run the model once. We tend to run the model lots of times and sort of get results over that. And we may also want to run lots of different scenarios as well. So we had this morning 5 different parameter values that you could change, things like the number of agents in the model, level of transmissibility, the probability that you're infected at the start of the model, all that kind of stuff. And you may want to test different combinations of parameter values. And MESA allows us to do both of those things together really easily, using a library that it calls Batch Runner. And all we need to do basically is to specify with Batch Runner which parameter values we want to remain the same, which ones we want to change, how many times we want to run the model for each combination, combination of parameter values, or a scenario, if you like, and for how long we want to run the model on each run. And Batch Runner will do the rest. So we basically set it off and say, these are the different things I want to test. I want you to run it for this amount of simulated time, and I want you to repeat each scenario so many times, and it will go away and it will do it for you. So I'm going to show you how you can do this. I'm going to be using a modified version of the code that we worked on this morning. This version of the code includes immunization. So there's a vaccination thing that originally, so last year when I delivered this session, basically the afternoon session was you building in this this vaccination stuff. So you expand the model that we took this morning, and you'd have a look at how you build vaccination into it. But and that's quite useful, but it's partly because I think it's good for you to kind of build your own model from scratch to get used to using this, and partly because I was so blown away by the ideas you came up with in the cellular automata session. I thought, actually, I think there's much more value in getting you to sort of build your own. So I've still provided you with the code, so you can see how you would build the vaccination stuff into this. It's no different to, there's no new concepts. It's the same principles as we were showing this morning. It's just there's new methods and new results that we collect about how many people are vaccinated, and there's new methods about getting vaccinated and things like that. So I provided that to you. That's in your repository now, and you can check that out in your own time. But just to flag up, that's the version of the code that I'm going to show you now, which I've also included batch runners on. So if you see a few differences, stuff that you don't recognize from the sorting, that's why it is. Okay. So first thing we're going to do, so up to now, basically, we've just expand that again. We've just used the disease run file, the module, and all we did was we launched a server. So we just had those 3 lines of code that just said from this disease server, which we wrote a separate .py file, import the server, here's the server port, and launch it. And that's all we did. And that's all you need to do for running it with a sort of live server. But what we're going to do now is we want to use the disease run module to run the model in batch. So we don't actually need the disease server.py file now. It's not going to use it, but it's still useful to keep that in place. And what probably a good tip for this, if you're going to be doing this for real, we could just comment out those 3 lines of code in the disease run file, so that if we ever want to show the model running as a live server, we can just re-enable that and comment out the rest of it. And of course, then we can just run the file and it'll run as a server. So that's really useful when you come to do this in practice, because you can, if you want to show somebody the model and how it plays out, you can just re-enable those 3 lines of code, push F5, and it'll run it on the server. So that's really useful. So we're just going to comment out that bit of the code for this. So now we're going to write the stuff, the new stuff for our disease run file. So first of all, we're going to import the libraries that we need. So I've commented that out, and I've put, you can see I've put little notes here that says use this section for watching the model run on a server of visualization, and then use this section for running the model in batch run. So you can just comment out the appropriate bits. So this is the bit that we're now going to use. So the first thing we're going to do is import stuff. The first thing I need to do is I need to import everything from my disease model file. So my disease model module that I've created here, that I'm going to import everything. So the asterisk there means import everything. So I'm just going to import everything for that, because we need the batch runner is going to need all of it. I'm also going to import something from NumPy called arange. It's just for 1 line of code down here. Arange is a useful little function of NumPy. Basically allows us to create evenly spaced numbers within a given interval, and we're going to use that, as I say, just for 1 line of code. But it's useful when we're doing this batch running stuff. We're also going to import matplotlib, so we can plot our results. So you're used to using this. Because we're not running it on the server now, we can't use MESA's visualization, the server-based visualization stuff. So if we want to plot some graphs at the end, then we can just use matplotlib as we normally would. And we're then, most importantly, we're going to import the batch runner class. This is the magical little class that will basically do all this for us and allow us to run things in batch and have different combinations. Okay, so that's the 4 imports. Everything from your model class, this NumPy arange function, which is just going to be useful in a minute, matplotlib, so we can plot something, and the batch runner class. So then what I'm going to do is I'm going to set up a dictionary. And this dictionary is basically going to store all of the attributes, all of the parameter values that I don't want to change. So all the ones that I want to keep fixed for all of the different scenarios that I'm testing, these are the ones that I want to stay the same throughout. Okay, so I'm just going to call it fixed params. Call it whatever you like. And I've set up a dictionary, and basically the dictionary just has key value pairs, with the key being the name of the parameter that needs to match whatever it is in your model. And and the value against that is the value that you want that will remain fixed. So here I'm saying I want the width and height of the grid, 10 cells by 10 cells, to be fixed. I don't want that to change across my different runs. I'm going to keep my initial infection rate at 0.8. I'll keep my transmissibility at 0.5. I'll have the mean length of the disease at 10, mean immunization duration at 20. So that's, again, a new aspect of the model where, as well as having a disease duration, you have an immunization duration, which essentially determines how long you are protected against infection, and a probability of being immunized, which is just at any bit like being infected. This is what I would have got you to do. This is just a 5% chance that on any given time unit you will become immunized. So those are all the things that I basically, they're my parameter values and, or the parameter names and the parameter values. So I'm saying I'll put all these in a dictionary, and then I can feed that into Batch Runner and say, don't change those things. Those are the things I want to stay the same. Okay. Then, as you might imagine, I'm then going to set up a separate dictionary, which will basically specify all the things that I do want to change. So these are the different scenarios, essentially, that I want to look at. What are the combinations of parameter values that I want to test? Okay, so I've called mine variable params. Again, you can call it whatever you like. And the two things I want to change in this model are the number of agents, which remember is n. Remember that needs to match the whatever you're passing into the disease model here. And the level of movement. Now, those are the only two things I'm going to change. Now, you may think, well, that's quite conservative. Why are you only changing two things? I'll come back to that because it's quite important. So as well as specifying, again, as we specify as a dictionary, and in the fixed parameters one, I basically had the parameter name and as the key, and then the value would be the fixed value that I want to remain constant. Here, we have the key as the parameter name, the same as before, but the value is the range of values that I want it to test. Okay, so what it'll do here, so for the number of agents, n, I want it to test all possible combinations, all possible numbers of agents between 2 and 100 inclusive in increments of 1. Okay, so it'll basically test 2 agents, then 3 agents, then 4 agents, then 5 agents, etc. So it'll test all those different scenarios. Here, for level of movement, I'm doing the same. Here's where I use the A range thing that I imported from NumPy, and that basically allows me to do this with floating point numbers and have equal increments. And so I can use A range for this, and I'm going to test levels of movement between 0 and 1. So 0 is never moving. 1 is you always, all agents move on every time step. And I want to test that in increments of 0.1. Okay, so it'll test everything from 0, 0.1, 0.2, 0.3, etc., all the way up to 1. Okay, so those are the different combinations. So for each, remember, these are different combinations. So the first thing it'll do is test 2 agents with a level of movement of 0. Then it'll test 3 agents with a level of movement of 0, 4 agents with a level of movement of 0, etc., etc. And then when it gets under 3 agents, it'll go back to this, etc. So so it's going to test all of those different combinations. So I've set up 2 dictionaries, my fixed parameters, these are the things I don't want to change, and my variable parameters, those are the things I do want to change. So these are the different scenarios that you'll be testing. Then I'm going to tell it a couple of extra things. So I'm going to set up a couple of parameter values here that I can just feed in when I set up the batch runner. So I'm going to set up my number of iterations to be 5. So that basically means for each combination, so if you're testing 5 agents with a level of movement of 0.6, run that scenario 5 times. Okay, so you're going to run that same combination 5 times. And here I've called num steps, which basically just means the number of time steps. So time steps are days in this particular model. So I've put 365. So basically I can run it for a year of simulated time. So for each of these combinations, it'll run that combination 5 times, and it'll run the model for each run for a simulated period of 365 time steps, or 1 year. Once I've got all that set up, I can then set up my batch runner. So I set up my batch runner. I've just called mine batch run. It's an instance of the batch runner class. So I set up a new batch runner, and here's the information that I pass into it. I pass in my model class. Remember, we've imported everything from disease model up here. So I can just refer to disease model because I've imported it. It now exists here. When you import something, it's as though you've written that code in this PY file, essentially. So I can just refer to disease model. Then I say my fixed parameters. Which ones are those? So I pass it the dictionary. I say equals fixed params. That's the dictionary I set up here. My variable parameters I set up here. So I've called that variable params. So I specify that. My iterations I set up here. So that's my num iterations. Max steps is this one, the num steps. And then I set up the model reporters. So these are the values that we want to track. Remember when we were doing this on a server, we looked at that in terms of plotting on a graph, but here this is the results that we want reported from our different combinations. So we use the same principle of using the data collectors, but we feed it in here instead, because remember that server isn't going to run this time. So I do it in the same way I did for the disease server when I was setting up the graph. I just specify a dictionary with the name of the result that I'm being collected, which remember we set up in the data collector, so it has to match. And the name of the method that will calculate that. So calculate number infected. So we saw this one this morning, total infected, and the method is calculate number infected. This one you won't have seen, which is total immunized, which is calculate number immunized. That's what I would have got you to do in the old exercise. But if I go back here, you can see, as well as that calculate number infected method that you created this morning, we also created a new method in here to calculate the total number immunized, exactly the same way that you did for the total number infected. So that sets up our batch runner. That creates a new batch runner, tells it the model that we want it to batch run, what parameters we want to stay the same, what ones we want to vary, how many iterations per combination, how long to run the model for each particular run, and which results we're basically interested in. Once we've done that, we just tell it to run. So we call the run all method on our new batch runner object, which I've called batch run. So we say batch run.run all, and that will then go through and it will store, it will run through all those combinations, and it will run them in the background. So you obviously not seeing a live visualization of it now, and it'll run it all really quickly, well, ish, depending on your computer. And it will then finish once it's gone through all these combinations. Once it's finished, we can grab out the results, and remember that we've told it what results we want. That's the results it will be collecting. Those are the model reporters we set up here. So we can grab that out once it's finished. We just call the get model vars data frame a method of the batch runner object. So I say batch run.get model vars data frame, and that will store it, basically stored in the pandas data frame, as the name might suggest. And so I'm going to take a copy of that and I'll store it in something called run data. So that's now going to be a pandas data frame. And what I can do is I can then plot a scatter plot here, the level of movement versus the total number infected. Okay, so you could do anything, but I'm just doing this for the purposes of showing you a graph that you could generate. Okay, so that's basically all there is to it, but there is a word of caution here. In fact, before I get onto the word of caution, let me start this running. So let's run the thing now, and it'll run through and throw me an error. That's helpful. Why is that done that? Calculate number immunized is not defined. It should be. If in doubt, restart the kernel. Sorry about this. Spider doesn't like me in the last couple of days. There we go. So that should have run. Okay, so I'll just talk over my incredibly loud computer fan, which you can now hear, which is now whirring through. So here you can see all, my God, that is going loud. You can see all of the iterations that it's going through, and you can see there's a lot. So it's already up, it's done 1,000, nearly 1,200 combinations now. It's doing about 30 to 40 iterations per second. So remember, an iteration is a particular combination of a parameter value combination. So this number of agents with this level of movement, and it'll do each of those things, run each of those combinations for 1 year of simulated time, and it'll do each of those things for five repeats. So there's going to be quite a lot of iterations. I'm just going to let that run in the background whilst my computer hopefully doesn't blow up. While I go back to say, because this is quite a timely thing, be really, really careful here, because agent-based simulation, I mean, this is a fairly simple agent-based simulation. Agent-based simulation is quite computationally complex, because essentially you're modeling lots and lots of agents all doing their own thing and interacting, and that causes quite a lot of strain on your computer, because there's quite a lot to do, and so you can very quickly get very complex agent-based simulations which take a lot of computing power, and if you then throw into the mix having lots of different combinations that you're running in batch, you can very, very quickly bring down even the fastest computers, because already, let's flip back, so we're up to nearly 3,000 iterations so far. These are just two things that I'm testing, but remember, it's got to do combinations of all of these things, so you can exponentially increase the number of combinations very, very easily. I forgot this the very first time I ran the training, and Mike had just, in work, we were still in the office back then, he had a brand new, very powerful computer, and I said, oh, I'll take it out for a spin, and I logged into his computer, remote logged in, and I tested some MESA combinations and completely forgot how many different combinations I was testing. He had a huge amount, I think it was like 64 gigabytes of memory. It was a 32 core processor. I brought it down within about 3 minutes. It didn't even do the first combination because it took all of its computing power to try and create the pandas data frame that would store the results, and then it just collapsed. Which was quite impressive, because only that morning he told me that I'd never managed to bring down his computer. So I guess I win. So just be very careful. Think about how many, you may just want to do a little calculation of how many combinations that's going to result in when you start testing lots of different combinations. And it might be safe, it's certainly safest to think about fewer combinations at the start, maybe even just change, sort of one parameter at a time, maybe until you feel a bit more confident about the things, or at least minimize the number of increments that you do for this kind of stuff, because there's lots of different combinations for that. That's still running, and you can see it's just slowing down. So what I'm going to do while that's still running, and keeping an eye on my computer and making sure smoke's not coming out the top, I will start explaining the exercise that you're going to do in a minute, and then hopefully by the time I've done that, the thing will have run. So what you're going to do now, basically for the next 2 hours, is you're going to work in your groups. Now, as I say, this is a smaller number of you today, because obviously we're in option sessions now. So if there's nobody else in your group, do join another group, because it's important you work in a group for this, really. So do join another group as a guest member. I'm sure everybody will be very happy to welcome you. What I want you to do is I want you to learn everything you've learned in this module, including the stuff in the cellular automata stuff, and all the skills you've learned today in developing MESA models, to design and build your very own agent-based simulation. So you can have 2 hours to do this. We're going to come back at 4, and you're basically going to ask each group to present their model and to demo it to us. So what I recommend is to do the following. First of all, discuss some, oh, my computer's gone quiet. Hooray, let me just flip back temporarily. So it's finally run, it's gone much quieter in here now. So the 4,900 iterations that it went through, and I've got a very fast computer, and that still took about 4.5 minutes to do that, so be warned. And of course, what it should have done is plot the figures. So let's have a look in the plots pane. And there we are. So I just got to do a silly little scatter plot, which I forgot to even label. That's helpful. I'm not running that again. Which is just basically plotting level of movement against total number of infected. And we can see very clearly, as you would expect, the more people are moving, the more numbers of total infected that we're getting on that scatter plot, which is exactly what we would expect. So that's batch running. Okay, so you can very easily do that, and you can see that all we had to do was to change our disease run file and put in those things, and that will allow you to do everything from there. So if you've already got your data collectors and everything set up, it's just a matter of putting some code into your disease run file, and it'll do all that for you. I wish SymPy had something like that, because it's really neat in MESA, and SymPy could do with exactly that. You can do it in SymPy, but you have to do it yourself essentially. So right, back to the exercise. So yeah, the way I'd approach this, I'd start by tossing around some ideas, have some potential problem areas you could use agent-based simulation to tackle. As you might end up plumping for the one you came up with last time in the cellular automata session. That's fine, but you might think of something new. I mean, obviously we've now you've been exposed to something else and seen a more sort of practical application of some of this stuff that might have fired off some new ideas. So do have a bit of a discussion first about some potential ideas for this. And then what I want you to do is choose one of those ideas and draw up a design for how the model will work. So think about what will be your agents. Remember, your agents don't have to be living, breathing organisms. Your agents can be organizations, or they don't even have to be individuals. They could represent groups, for example. So think about what your agents will be. What behaviors are you going to have? How will your what will essentially be your behaviors for your agents? What movement patterns will they have? Will they interact with each other? And if so, how? What are your cells representing? What kind of cell neighborhoods you'll have? Think about all of that kind of stuff. So draw up a bit of a design for how that's going to work. And then once you've done that, I then want you to build a prototype dummy model using MESA. Now, I appreciate in most cases, you're probably not going to have all the data you need to actually build a realistic version of this. So you'll probably have to make up most, if not all of it. And maybe you will, but you'll probably have to just make up a lot of stuff. But it should be enough to build a sort of dummy prototype of this is how it would work. And that's basically what I want you to do. That's the core idea behind this, to have a go at building something in MESA. Put on a nice little interface, include some user interface elements, things like sliders. You can check out the I'll link you to the MESA documentation as well. So if you want to put in any other fancy interfaces, you're welcome to do so. And visualize maybe some graphs, put in some sliders, your grid, etc., and allow the user to play around with different aspects of your model. Think about what different things you'd want the user to play with. So you've got 2 hours. At 4 o'clock, I'm going to bring everyone back, and I'm going to ask each group to present their models. And I'm also going to ask you all to share them on Slack, your model code, so that other people can play with them too. And I have high hopes of this. I think your designs last time were excellent. And hopefully you've learned enough today that you'll be able to actually build stuff like that. So I'm really looking forward to seeing what you come up with. Any questions about any of that? No, great. Okay, in which case, go forth and be creative. And I will, as always, bounce around the rooms. Make sure, obviously, in the next 2 hours, you do take some sort of break within there somewhere. But have fun. And as I start by discussing some ideas with your groups, then choose one of those ideas and build up a design, and then turn that into a MESA model. Brilliant. I'm really looking forward to this. So let me stop sharing. I'll stop talking, and let's open up the rooms. Hi everyone. Okay, welcome back. So I let you go a little bit longer because I can see there were a few groups who were so close and nearly there, and I just wanted to try and give you a little bit of extra time just to fix any sort of last minute errors. And I know one group did, I saw another group that didn't. So don't worry if you didn't quite get there. Just sort of present what you managed to do, what you're trying to do. If you didn't quite manage to get a finished article. I had a look. I think we only had 5 groups, which I've made a note of. So we'll just go through them in order. So if we can start with Deep Thought, because I think Deep Thought did have a working model eventually. So does someone from Deep Thought want to share what they've done?
Yes, I think, let me just share my screen. And then frankly, I think the output is more impressive than the code used to create it. Hang on, let's just check that's the right one. So hopefully you can see that.
Yep, that's all coming up.
Cool, okay. 2 seconds, caller. Let me just do that one and run it. Okay, so ours was obviously after feeling for Dan the other week when no one did the zombie apocalypse. We thought we would do the zombie apocalypse, and basically we have zombies. We have people some who will hold the cure. So if they're holding a cure, and they land on the same spot as a zombie, then there's a probability that a zombie will actually be cured and become a normal person again. But they lose one of their cures every time they try and use one, whether it's successful or not. So obviously, eventually, they'll become a normal person. And then based on the parameters we've put here, it all just descends into zombie apocalypse, which is pretty much what you want. But we included a number of factors you could control, such as the probability of starting as a zombie, the probability of starting with a cure, assuming that you're not a zombie, obviously, the maximum number of cures that you could be allocated. So there was just a random uniform distribution to decide if you were going to have cures, how many you could have. And then the other ones we've seen before, like transmissibility and level of movement, we essentially left as the same.
Fantastic. That looks absolutely great. I love that. So there were two groups I saw that did the zombies, and it was really interesting when I first went into the groups I was bouncing around, that I saw your group was talking about, having people having cures and trying to cure the zombies, and then I went into the other group and they were talking about what weapons can we give people. So it's fantastic to hear you coming from very different directions, but fantastic. That's really nice, really good, and I love your visualization there on the grid. I think that looks really cool. I just wish somebody will put in a zombie apocalypse project proposal, just as a let's be on the safe side. Nobody was prepared for this pandemic. Maybe we should just have a zombie apocalypse model just in case. So you never know. That's be great to see that. Cool. That's fantastic. Thank you very much. Okay, I'll move through. I think Holly, did somebody from Holly want to present what they were doing?
Yeah, I'll have a go. Right screen. So yeah, we did consider zombie apocalypse, but we decided to stick with the disease. Let's not call it COVID transmissibility model. But we thought we'd give it a tweak that we talked about when we did the previous session, and split it into two different countries. So we've got our grid here, but we've got two different countries with C in between. So yeah, with a bit of helpful suggestion from Dan, we created some. So these are actually agents, but they don't do anything. They just sit there and they're C. We turned off the toroidal thing because we've got some people jumping and teleporting from this part of the country elsewhere. So people can move about within their country. We just stuck these numbers on because we thought at first people were leaping about a bit, but we reassured ourselves that they were moving correctly. So people can move out within their country as before, but the only way of moving from one country to another is this sort of 1 in 8 chance across here. So depending on what parameters, it behaves quite differently. Sometimes there you go, you've got really quick cross-border transmission that time. But often, let's try another go. Oh, sorry, we didn't have anybody infected to start with there. When we've got probability of initial infection, but we only allow country A to get infected first. Maybe I've got my infection level a bit low. There we go, we've got somebody infected there. So, oh, that's died out already. Anyway, tried this loads of times. And these seem like good parameters. There we go. So often you get the one country quite heavily infected first, but it takes quite a while to spread across the border. And obviously that's affected by your level of movement and so on. But there you go, it's gone across there now. And also infected the other country.
That's brilliant. I really like that. That's really cool. And you can imagine, so that's a really neat way. I like what where you've thought about the grid and how that grid sort of represents the environment, and having blocked things on your grid and using that to represent different countries and having a border. And you could imagine, translating that into modeling, COVID transmission in a hospital or something, and having different ward structures, so having almost shapes on your grid where they can transmit and move. So no, that's really nice. I like that. I like that a lot. I think that looks really cool, and a really nice visualization as well. That works really effectively, and I like the little numbers there as well. I think that's quite nice.
One thing we really wanted to do, but looking at documentation, couldn't see how, is where you've got sort of 5 people all in the same cell. You can't easily see that, so it didn't look as though there's a. You would think in the portrayal method, it would, it could jitter them, but it doesn't seem to. So I think you'd have to sort of manually do your own sort of sizes or something like that to
Yeah, that's a good question. I've never looked at that, and I just assumed that you could do that. That you could, sort of displace them so they're not drawn from the center.
See how.
Yeah, I'll have to have a look at that. Because yeah, you would think that it should be in there. If not, there'll be I'm sure there's a way to reverse engineer it so that you can. But yeah, you're right. I mean, that's particularly where you've got things where you've got people in the same cell. You may want an intelligent way to model more than two. Because I mean, you could have, I guess you could have different shapes and different sizes, and you could probably get maybe 3 or 4 in the same cell visualized differently. With sort of decreasing sizes, but beyond that you're going to struggle, I think. So
yeah, unless you can do transparency, I think they just also go on top of each other.
Yeah, that's another good point. Yeah, I'll have to check that out. I don't know offhand, but no, that's really good. I really like that. Thank you. That's excellent. Cool. These are really great ideas. Okay, Max, you're up next.
Hello. I think Antonia's having trouble with her.
Yeah, no, I'm here. I'm here.
Okay.
I got it running sort of, but
Oh, good. Me too.
with issues.
There's just 2 of us.
Maybe share yours.
Yeah, I found one more bug. But so we tried to do the disease model with a region on the grid reserved as a hospital. So if I share my screen for the last time it ran, which unfortunately we don't seem to be keeping the hospital people in the hospital.
Oh, they keep escaping.
So our bottom line is meant to be reserved for the hospital. So if I reset, you see I have blue dots, and these are meant to be hospitalized susceptibles. And then they just disappear. So I think something about our movement logic is not working properly, and our hospitalization.
That's interesting, because I had a really different problem. So my hospitalization is fine, but everyone just stops being infected after like 2 steps, and I don't know how, because we didn't manipulate anything on the infection, so I'm not really sure how I messed that up, but we're very close.
It sounds like you're almost there. Yeah.
Yeah. We could yeah. So yeah, we had to play around. We had to take out the more neighborhood because we needed to skip people when they moved, to skip over the bottom row if they were not hospitalized. And then if they were in the hospital, they could just move left to right and stay on row 0. But we haven't managed to quite finish it yet. So.
Yeah, that should certainly work in theory. I bet it's just something very simple that's gone wrong. It's always quite difficult to debug these things.
Well, we debugged quite a lot of very simple problems already, so I think we just made lots of very simple mistakes. But we're getting there. It was good fun.
It's always tricky. And a question came up actually in one of the groups, and it's a good point. So when you're doing object-oriented programming, it can be a little bit more difficult to try and debug things because, of course, you're sort of building up, and you're creating objects, and they're not so easy to sort of work with. One, obviously, in most cases, I think all the groups essentially adapted the code that you looked at this morning. In reality, what you'd probably do is to start this thing from scratch. You may copy and paste bits in, but you would gradually build it up. So you sort of build up. I'll create my person class first. Now, the first thing I'll do is set up the constructor. Now I'll run that, and then in the console, I can then create a new person with these attributes. Has that worked? And then check it sort of bit by bit. But obviously it's difficult when you're adapting existing code, because the second you change anything, you've broken the whole thing until you fix it all. So it's always tricky. But yeah, certainly if you were doing this for real, I would start from fresh. You can copy and paste bits in, but then just gradually build it up. Brilliant, thank you. That was really good. Okay, Robocop, you're next.
Yes, so we tried to put in a second variant into our model. If I share my screen, start this. So you just have a second initial infection rate, transmissibility rate, and mean length of disease. And then you can kind of play around with the parameters and see if one outcompetes the other. yeah, just see where it goes.
That's really cool. So I like that. So you've got a sort of variants competing for dominance. So it looks like your variant B is dominating there very much. That's really cool. I like that. That's a nice extension of the disease model, and exactly the sort of thing that you may want to model for exactly what's happening now, unfortunately. No, that's really nice. I like that. And a nice, simple but effective visualization. And it's really good that you're using these visualizations powerfully in MESA, because it's really good for this kind of stuff, I think. Brilliant, thank you. Okay, so we've got two more. So Marvin, do you want to go up next?
Yeah, you have to use your imagination a little bit with our one. We had lots of issues with server stuff that we didn't overcome.
Yeah, no, that's cool.
But essentially, we tried to do this spirit of Christmas, I suppose, and how Christmas cheer would spread amongst people who already like Christmas. Then we also had another kind of agent being those that are Scrooges, and you could change how effective they were at changing people to be not Christmassy. And there would have been black in the grid, but we couldn't get the grid connected for some reason. And then we were going to move on to have like static points that would have been either Christmas choirs, or I think we wanted to do like the Coca-Cola truck moving around and doing stuff. But yeah, we were a bit stumped for some reason. It just didn't work out. But that was, if you can imagine that on the grid, then that was what it was meant to be.
That's really cool. It's a great idea. I love that. What I like about that as well is you could imagine that working as a kind of proof of concept to then show something like, the way people feel about vaccinations or something like that, and spread of a particular idea, and you might have people that are trying to sort of inhibit that and people that are promoting it, and how that sort of interplays. So you could imagine doing a really nice thing around that. I suspect. So here's the thing about MESA, and I think virtually every group ran into this. When you get that blank grid, it's usually nothing to do with the grid. It usually means there's something wrong in your code. And if you get that, if you then go back to Spider, in the console, buried, there'll be usually an error message, and it'll usually indicate, there'll be one line in there that'll indicate, and it's probably something to do with, in most cases, it's usually the one of the classes you've either not passed in enough arguments or too many or something like that. And MESA will run the server, but then it'll just, when it gets to drawing it, because that's the point at which it starts the model, it just doesn't. So it's something early on. It's probably something really simple, and it's probably not related to the grid. It's probably related to the model, just a very simple oversight. So yeah, hopefully that might help you debug that. Brilliant, thank you. That was really cool. And then last, we've got Talkie Toaster. So this is the other zombie group. So do you want? I know you were having last minute issues trying to get it working. I don't think you quite got there, unless you've managed to fix it. But
yeah, you're also going to have to use your imagination with ours, I'm afraid. So we actually scaled it back to try to get it to work in the first place. So it was just zombies and humans, and these zombies could infect the humans, and the zombies can't die yet. So the thought was that eventually we would have a probability within the code of whether a human had a weapon or didn't, or even if they could kill the zombie or not. We haven't quite worked that out yet. But if eventually there would be a collection where it would say whether or not the humans won or the zombie apocalypse had taken over. So.
That's brilliant, cool. What I liked about this one as well, what you're trying to do was this sort of dynamic of having them run away. So
yes,
you essentially have people that would try and choose, if they saw a zombie, would kind of move away from them.
Yeah, and we have the zombies, if they see a human within their radius, will move towards a human as well.
Yeah, that's really nice. That kind of dynamic, the kind of gravity dynamic, where you're gravitating towards something, or being pulled towards something, or being pushed away from something, can make really interesting dynamic models. And in fact, so the zombie thing is used quite often for teaching agent-based simulation, and there's some great zombie models that you can get out there. And it's fantastic when you see one of those working where they're sort of running away, and you just see them sort of they're very often just sort of cluster. They either go into the corners, or they just sort of cluster in one location, and then just gradually the zombies descend and take over. So they're really interesting models. So I don't think you're too far off. I think looking at your code, I think there's just something in that middle bit in one of your methods that's wrong, and then it'll work, I think. But as ever with these things, it's always so frustrating when you get so close, but you can't quite get it there. But yeah, fantastic stuff that you've done this afternoon. And if you want to carry on with those in your groups, and you do manage to get them working, because I think most of you are nearly there if you didn't get there, then do post them on Slack. And those of you that did get a working model, post them on Slack on the public channels, so that people can have a look at them as well. I think they're great, really good stuff you've done today. So that's it. So thank you for coming along today. Hopefully it's given you a bit of a glimpse into how you can do this agent-based simulation stuff. Hopefully you've seen it's not too complicated using MESA. Actually, you can do this stuff fairly easily, and really a lot of it is just sort of designing it and thinking about how you're going to set up your agents, what they represent, and what your environment represents, and all that kind of stuff that goes alongside it. But actually MESA is really good at being able to put those things into practice. So hopefully we might see an agent-based simulation idea or two in the project proposals. Would be fantastic. Otherwise, I will close off there. Just a reminder, next week, so you've only got one more session with me in phase 1. Obviously, you'll have another 3 in phase 2 when I actually write them. And I'll post up more information about that. But I'll be doing system dynamics next week on Tuesday, I think it is. Yeah, Tuesday. And you've also got a GeoPandas session, which Mike's posted some information about. The Wednesday session, Luca, our guest lecturer, is going to be delivering that. He's on leave at the moment. He's going to post, I think, the information on Monday that you need for that. But I don't think there's anything, it's basically an R, and there's not much you need for that other than downloading the materials. And then Sean will post up the stuff for his session on Thursday. Okay, cool, excellent. Let's close off there. Have fun, everyone, and I'll see you next week. And don't forget about your project pitches. So you've got about a week and a half to get those together. Don't overthink them. Just nice, simple 2-minute video, just capturing what you're going to do, and all the stuff that we sort of hinted at you should include. But I look forward to seeing what ideas you come up with. It'll be really good. Cool. Thanks, everyone. Bye-bye.